Hello there, and welcome to Science for Sleep, where we take complicated ideas, give them a comfortable chair, and allow them to explain themselves without raising their voices. Tonight, we are looking at a black hole that appears to be doing something black holes are not usually thanked for doing. It is helping to create stars. That sentence sounds slightly wrong at first. Black holes are normally introduced as the great destroyers of space. They swallow gas, tear stars apart, bend light, distort time, and make nearby matter extremely unhappy. They are rarely described as productive members of the cosmic community. Yet far beyond our galaxy, a supermassive black hole is racing through space with a long trail of newborn stars behind it. The trail stretches for about 200,000 light-years, making it larger than the visible disk of the Milky Way. It was not drawn there by an artist with an unusually large ruler. It was found in real observations made with some of our most powerful telescopes. The object is known as RBH1, short for Runaway Black Hole 1. The name is practical, which is probably wise. When you have found a black hole moving at almost 1,000 kilometres per second, there is no need to make the paperwork more dramatic. The object is already doing enough. Before we get closer to it, where are you listening from tonight? Perhaps you're in a quiet room with the lights turned low. Perhaps there is traffic outside, rain against a window, or a neighbour who has chosen this exact moment to reorganise a cupboard. And what time is it where you are? Somewhere, this video is beginning in the evening. Somewhere else, it may be starting after midnight. Meanwhile, the light carrying the evidence of RBH1 has been travelling across the universe for billions of years, arriving at our telescopes long after the events we're seeing actually occurred. If you find this kind of slow scientific journey relaxing, you can give the video a like and subscribe to the channel. It helps more people find this quiet corner of astronomy, including those who enjoy learning about violent cosmic events in the most peaceful way possible. There is something pleasantly unreasonable about falling asleep while a supermassive black hole crosses intergalactic space at several million kilometres per hour. Still, bedtime has always involved a certain amount of trust. Settle into whatever position is comfortable. Let the day become less demanding for a while. There is no test at the end, no equation to memorise, and no requirement to keep track of every number. We are simply going to follow a thin streak of light across an old Hubble image and see where it leads. The story began with something that did not look important. In an image taken by the Hubble Space Telescope, astronomers noticed a narrow, straight feature extending away from a distant galaxy. Space images contain all sorts of unwanted marks. High-energy particles can strike a detector and leave bright lines. Reflections can create odd shapes. Processing errors can produce features that belong to the camera rather than the universe. A suspicious streak is often less exciting than it appears, rather like discovering that the mysterious light in the garden is only a solar lamp you forgot buying. This particular streak refused to go away. It appeared in more than one observation and behaved like a real astronomical object. Follow-up measurements showed that it was not a scratch, a cosmic ray strike, or a conventional jet blasting from an active galactic centre. It was a long structure containing young, hot stars and glowing gas. At one end was a compact galaxy. At the other was a region with unusual motion and ionisation, as though something massive and fast had pushed violently through the surrounding material. The narrow feature extended for approximately 62 kiloparsecs, or about 200,000 light-years, from a compact star-forming galaxy seen at a redshift of roughly 0.96. Spectra collected with the Keck Observatory revealed a mixture of ordinary star formation and fast shocks. The colours of the stars also changed along the structure in a way that suggested their ages increased with distance from the leading tip. Those observations led astronomers to propose that a supermassive black hole had been expelled from the galaxy and was forming stars as it crossed the surrounding gas. Hubble had captured the shape of the mystery. Later observations began to explain it. Ground-based spectroscopy revealed that different parts of the streak contained gas moving at different speeds. The James Webb Space Telescope then examined the tip in much greater detail. Webb found a sharp change in gas velocity across a region only about 1 kiloparsec wide. It also measured the light produced by several elements in the gas, including hydrogen, oxygen, nitrogen, and sulfur. The ratios between those emission lines matched the behavior expected from a fast radiative shock. Together, the shape, movement, and ionization of the gas supported the idea that a massive object was traveling supersonically through the thin material surrounding the galaxy. The inferred speed was about 954 kilometers per second, with some uncertainty on either side. The energy required to drive the shock and maintain the wake suggested that the hidden object had a mass of at least 10 million suns. Nothing bright enough to account for that mass was visible at the tip. The object did not resemble a star cluster, a jet, or a stream of material pulled from another galaxy. A runaway supermassive black hole provided the explanation that best matched the combined evidence. It is worth pausing over the phrase hidden object, because black holes do not normally appear as black circles in telescope photographs. A black hole is defined by a boundary from which light cannot escape, so the black hole itself remains dark. Astronomers detect one by watching what happens nearby. Gas may become hot as it falls inward. Stars may orbit an invisible concentration of mass. Light from a more distant object may be bent by the black hole's gravity. In the case of RBH1, the main evidence is not a glowing ring of material falling into the black hole. The evidence comes from the effect of its movement through the surrounding environment. The black hole is detected through the disturbance it creates. Imagine a boat moving quickly through still water. The boat pushes water aside, building a curved wave at the front and leaving disturbed water behind. You might also imagine an aircraft travelling faster than sound and compressing the air into a shock wave. RBH1 is not moving through water or ordinary air. It is travelling through extremely thin gas around and beyond its former galaxy. That material is far less dense than anything we experience on Earth, but even very sparse gas matters when the object pushing through it has millions of times the mass of the Sun. A bow shock forms ahead of the motion. Gas entering the shock is compressed, heated, and forced into a different physical state. Behind the shock, part of that gas can begin to cool. As it loses heat, gravity can pull denser regions together. Those regions may collapse, fragment, and eventually form stars. The trail is not made from material leaking out of the black hole. The black hole is not distributing finished stars as it travels, like a cosmic delivery service with unusually severe working conditions. Instead, it changes the gas that was already present. Its movement compresses the material and creates places where star formation can begin. That distinction is important. Black holes do not contain a warehouse of stars waiting to be released. The newborn stars form because the surrounding gas has been disturbed in a useful way. Compression can encourage star formation when the gas becomes dense enough and is able to cool. Too much heat or turbulence may prevent collapse. Too little compression may produce no noticeable result. RBH1 appears to create a moving region where the balance briefly favours the formation of stars. This process is unusual, but the basic physics is not completely unfamiliar. Shock waves from exploding stars can compress nearby clouds. Colliding galaxies can squeeze enormous reservoirs of gas and trigger intense periods of star formation. Spiral arms can organize gas into denser regions where stars are more likely to develop. What makes RBH1 extraordinary is the combination of scale, speed, and cause. A supermassive black hole, expelled from its home and travelling through the gas outside it, appears to have produced a star-forming line extending across roughly 200,000 light-years of space. A distance that large is difficult to picture, because human intuition becomes less helpful once we leave familiar scales. A light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers every second. The wake behind RBH1 is so long that light would require about 200,000 years to travel from one end to the other. Even light, which can circle Earth more than 7 times in a single second, would need a period longer than all of recorded human history to cross the trail. If a signal began travelling from one end when early modern humans were spreading across Earth, it would only now be approaching the other side. In a Hubble image, however, the whole structure fits into a thin mark. This is one of the strange effects of observing extremely distant objects. Immense structures arrive on our screens as small shapes. A galaxy containing billions of stars may appear as a soft oval, only a few pixels wide. A trail larger than the Milky Way can resemble a line that someone might remove while cleaning an image. The black hole's speed is equally difficult to appreciate. At about 950 kilometres per second, RBH1 would cover the approximate distance between London and Edinburgh in well under a second, assuming we ignore the atmosphere, the ground, and several important rules about where black holes should be permitted to travel. Its speed is greater than 3 million kilometres per hour. A passenger aircraft moving at its normal cruising speed would need several months to cover the distance RBH1 travels in a single hour. Yet even at this enormous velocity, the black hole requires tens of millions of years to produce a wake measuring 200,000 light years. Space has a reliable way of making extreme speed appear patient. The stars along the trail did not all form at once. Different regions were affected as the black hole passed through them. Material near the galaxy was disturbed during an earlier stage of the journey. Gas closer to the moving tip was encountered later. As a result, the position of the stars along the wake contains information about when they formed. The structure acts as a record of the black hole's movement. A camera can record the path of a moving light as a bright streak during a long exposure. RBH1 cannot draw a line directly because the black hole itself produces no visible light. Instead, it changes the gas along its route, and that gas later becomes visible through glowing material and young stars. The line shows where the black hole has been, even though the object that produced it remains hidden. There is a useful irony in this. If the black hole had crossed a completely empty region, we might never have found it. An isolated black hole does not shine simply because it exists. It becomes detectable when matter reacts to its gravity or movement. The surrounding gas acts rather like powder, brushed over an invisible fingerprint. Without the powder, the pattern stays hidden. Once the material responds, the shape becomes visible. This raises an interesting possibility. If one runaway supermassive black hole has been detected because it happened to pass through enough gas to create a bright wake, others may be travelling through quieter regions without leaving such obvious evidence. They could move between galaxies for billions of years, remaining dark and extremely difficult to find. RBH1 may be a very rare object. It may also be one member of a larger population that is usually invisible. At the moment, astronomers do not know which possibility is correct. This particular black hole may simply be more considerate than most, because it has left a clear record of its route. The word runaway can also be misleading. The black hole did not make a decision, pack a small suitcase, and leave after an argument with its galaxy. Something gave it an enormous kick. Supermassive black holes normally remain near galactic centres, because that is where matter settles into the deepest part of a galaxy's gravitational field. Moving one far from the centre requires a major event. Accelerating one fast enough to escape the galaxy entirely requires something even more energetic. The leading explanation involves a merger between two supermassive black holes. Before that merger, each black hole probably occupied the centre of a separate galaxy. The galaxies approached one another, interacted, and began to merge. Their stars and gas became mixed, while their central black holes gradually moved toward the centre of the combined system. The black holes eventually formed a close binary. As they orbited, they lost energy by producing gravitational waves. Their separation decreased, their speed increased, and the orbit became tighter. During the final stage, the two black holes merged into one. Gravitational waves carried energy and momentum away from the system. If those waves were emitted equally in all directions, the newly formed black hole would remain close to the centre. A perfectly equal distribution, however, requires a very balanced merger. Real black holes can have different masses, different rates of spin, and spin axes pointing in different directions. When the gravitational wave emission is uneven, more momentum leaves in one direction than another. Conservation of momentum then causes the merged black hole to recoil in the opposite direction. The result is often called a gravitational wave kick. This is similar in principle to the recoil of an object that throws mass backward, although no ordinary material is acting as exhaust. The momentum is carried away by ripples in space-time. During a sufficiently uneven merger, the recoil can be powerful enough to move the new black hole out of the centre of its galaxy. Under extreme conditions, the kick can exceed the galaxy's escape speed and send the black hole into intergalactic space. The strength of the kick depends on the masses and spins of the original black holes. A balanced merger between non-spinning black holes would produce a relatively modest recoil. Unequal masses, rapid spins, and particular spin orientations can create a much stronger kick. Recent modelling based on RBH1's measured velocity suggests that its parent black holes were probably not a simple, neatly aligned pair. Their spins may have been tilted and precessing. The more massive black hole also appears to have required a high spin. The estimated mass ratio suggests that one black hole may have been up to several times more massive than the other, but not overwhelmingly larger. The modelling places the merger at roughly 70 million years before the stage we observe. The final coalescence would have happened rapidly, but the events leading to it developed over a much longer period. Galaxies had to approach and merge. Their central black holes had to lose orbital energy, move inward, form a binary, and cross the remaining distance between them. The galaxy associated with RBH1 is referred to as GX in current research. It is a compact, star-forming galaxy, seen as it existed when the universe was considerably younger. The properties inferred for the original black hole suggest that GX may itself have formed through a major gas-rich merger between galaxies of comparable mass. A gas-rich merger would provide both the central black holes and the disturbed environment needed to bring them together. Gravitational interactions between stars and gas could remove energy from the black hole's orbit. As their separation decreased, the binary would eventually begin losing significant energy through gravitational waves. This identification also clears up a naming confusion that appeared in some recent descriptions of RBH1. The runaway black hole has occasionally been connected to a separate system known as the cosmic owl or infinity galaxy. The cosmic owl is another unusual interacting galaxy system involving several black holes, and some of the same researchers studied both objects. RBH1, however, is associated with GX at a redshift of about 0.96. It is not the displaced black hole observed in the cosmic owl system. The supported account remains remarkable. A compact galaxy formed through a violent merger may have lost the black hole that once occupied its centre. That black hole now appears to be travelling beyond the galaxy while causing stars to form in the gas it encounters. Normally, astronomers describe the relationship between a galaxy and its central black hole as a long partnership. A black hole can grow by consuming gas from its surroundings. As the gas falls inward, it heats and may produce enormous amounts of radiation. Powerful winds and jets can then carry energy back into the galaxy. This exchange is known as black hole feedback. It can affect the temperature and movement of galactic gas, changing the rate at which new stars are able to form. In some cases, energy from an active black hole heats or removes gas and reduces star formation. Under other conditions, pressure from an outflow or shock may compress gas and help trigger it. The outcome depends on the density, temperature, chemical composition, and movement of the gas. It also depends on how much energy is delivered and how quickly that energy can escape. Astronomy rarely offers a simple rule when several complicated possibilities are available. RBH1 takes this relationship out of the galactic centre and turns it into a moving experiment. Instead of sitting in one place and affecting gas around a nucleus, the black hole enters new material continuously. Each region encounters the shock, becomes compressed, changes temperature and begins mixing with the surrounding medium. Some of that material cools after the black hole has already moved farther ahead. Dense pockets then begin collapsing. By the time stars appear, the black hole that helped trigger their formation may be thousands of light years away. The phrase, black hole creating stars, is therefore useful, but it needs a small scientific explanation. The black hole is not manufacturing stars directly. It is creating conditions that allow existing gas to form them. A match does not provide the wood in a fire, but it changes what the wood is doing. RBH1 does not supply most of the material in its wake. The gas was already present around the galaxy. The black hole supplies movement, gravity, and shock energy. The gas supplies the material from which the stars form. Those newborn stars are hot and blue. Massive blue stars use their nuclear fuel quickly, so their presence tells astronomers that star formation occurred relatively recently. These stars are short-lived compared with smaller stars such as the Sun. Some may survive for only a few million years before exploding as supernovae. The stars may be forming in groups and clusters along the wake. Around some of them, disks of dust and gas could eventually produce planets. The most massive stars will manufacture heavier elements and scatter them when they die. Material that began as thin gas outside a galaxy may therefore develop into a series of compact stellar environments. This does not mean every new star will survive indefinitely, or that every part of the trail will remain bound together. The wake may disperse over time. Stars may drift away from one another. Some may eventually return toward the galaxy's wider gravitational environment, while others could remain in intergalactic space. The discovery offers a rare opportunity to watch star formation occurring far outside the familiar setting of a galactic disk. Most stars are born in dense molecular clouds inside galaxies. RBH1 shows that the gas surrounding a galaxy can also form stars when a sufficiently powerful disturbance passes through it. Of course, the phrase, sufficiently powerful disturbance, is doing a considerable amount of work. The gas had to be dense enough to respond to the shock. It had to cool quickly enough for gravity to take over. The black hole had to move at an appropriate speed, and the viewing angle had to reveal the resulting structure. Hubble also had to image the correct field. Someone then had to notice the narrow feature and resist deleting it as an artifact. Ground-based telescopes had to collect spectra from the faint structure. Webb had to observe the leading tip with enough detail to detect the sudden change in velocity and the chemical signs of shocked gas. Scientific discoveries often sound inevitable once the explanation is known. Before the answer is available, the evidence can look like a thin line that should not be there. That is one reason this story is worth examining carefully. It is not only about a fast-moving black hole, it is also about how an unusual observation becomes a supported scientific explanation. A strange shape first becomes a candidate. Researchers compare it with known objects and instrumental problems. A jet from an active galaxy might create a long straight feature, so the expected properties of a jet must be tested. A tidal stream of stars might extend away from a galaxy, so its width, colour, and movement must be compared with the observations. Each explanation makes different predictions. A runaway black hole should produce a shock near the leading end. The gas should show abrupt changes in velocity. The line ratio should indicate shock heating. Stars along the wake should have ages connected to the black hole's movement. Better instruments can then search for those details. Webb's observations found the sharp velocity change, shock geometry, and emission line ratios expected from a supersonic object. They also helped explain the movement of gas farther down the trail. Shocked material gradually cools and mixes with the surrounding gas, creating a changing velocity pattern behind the black hole. The evidence does not allow astronomers to photograph the event horizon directly. It does something more practical for this particular case. It shows the physical response of the environment to an object with the required mass and speed. There are still questions. Astronomers want to understand exactly how the original black holes formed, how their spins were arranged, and how frequently such strong gravitational recoils occur. They also want to determine how the star-forming wake will change over time. Researchers do not yet know whether RBH1 is permanently unbound from its original galaxy, or whether the wider gravitational environment could alter its path. Its measured velocity strongly supports escape, but mapping the complete system remains difficult at such a distance. Other runaway black holes may already be present in telescope archives. Their wakes could appear as narrow streaks that were dismissed, overlooked, or classified as different objects. Future wide-field surveys will photograph much larger portions of the sky while maintaining enough detail to identify unusual structures. Computers may help search those surveys for long, thin trails. That task sounds simple until one considers the number of satellite tracks, detector artifacts, gravitationally stretched galaxies, jets, and ordinary image problems that can produce lines. Computers, like people, must first be taught the difference between an important anomaly and a detector having a difficult afternoon. For the moment, the central evidence is simple enough to hold without effort. Hubble found a line of young stars where no ordinary line should have been. Ground-based observation showed a mixture of star formation and shocked gas. Webb later found a supersonic bow shock at the leading tip. The best explanation is a supermassive black hole with a mass of at least 10 million suns, moving through thin gas at close to 1,000 kilometres per second. Its passage compresses that gas. Some of the compressed material cools and collapses, producing new stars along the route. We often describe black holes as endings, because much of what happens near them involves matter falling inward. Stars can be torn apart, gas can cross an event horizon, light can enter regions from which it will never return. RBH1 does not change any of those facts. It shows that the effect of a black hole depends on what it is doing and where it is doing it. Gravity that destroys one object can organize the movement of another. A shock that initially heats gas may also compress it enough for later cooling and collapse. The merger that expelled the black hole removed it from its galactic center. That same expulsion caused it to cross a large reservoir of gas. The collision with that gas then produced a wake in which stars could form. Nothing about the black hole became gentle. It did not change from a destructive object into a friendly one. Nature does not assign intentions to gravity. The same physical processes can produce very different outcomes under different conditions. How did astronomers recognize the strange blue streak extending from GX as a meaningful feature? The trail first appeared while astronomers were looking at something else. This happens more often in astronomy than we might expect. A telescope is pointed toward one object, the data arrive, and something unrelated appears near the edge of the image. The unexpected object may turn out to be ordinary. It may be a distant galaxy, a foreground star, or a mark created by the detector. Occasionally it becomes the reason everyone forgets what the telescope was originally supposed to study. In September 2022, the Hubble Space Telescope observed a nearby dwarf galaxy called RCP-28. Peter van Dokkum and his colleagues were interested in faint star clusters around that galaxy. They were not searching for a runaway supermassive black hole. There was no carefully planned hunt involving a list of suspicious galaxies and a large board covered in red string. They were simply examining the images and checking the quality of the data. During that inspection, Van Dokkum noticed a thin streak. It was narrow, nearly straight, and unlike anything he expected to find in the field. His first reaction was not that Hubble had discovered an enormous black hole crossing intergalactic space. His first reaction was that a cosmic ray had struck the camera. That was a sensible assumption. Cosmic rays are high-energy particles that travel through space and sometimes hit telescope detectors. When one strikes a camera sensor, it can produce a bright spot or a thin line. These marks have nothing to do with the objects Hubble is observing. They are temporary effects inside the instrument. Astronomers deal with cosmic ray marks regularly. They take multiple exposures and compare them. A real star or galaxy appears in the same place each time. A cosmic ray strike usually appears in only one exposure. because the chance of another particle hitting exactly the same pixels is extremely small. The unwanted mark can then be identified and removed during image processing. The suspicious streak appeared in both of the filters used for the observation. Hubble had photographed the field through two different broad filters known as F606W and F814W. Each filter records a different range of visible and near-infrared light. The exposures were taken separately. A cosmic ray might leave a line in one image, but it would not normally produce the same long structure in both sets of data. The line was still there. It was not a temporary particle strike. It was not removed when the images were combined. It had structure, colour, and a clear relationship with a distant galaxy at one end. Something in space had produced it. This was the first important change in the investigation. The streak moved from the category of irritating camera problem into the much more interesting category of thing that should probably not exist. The image itself did not look spectacular in the usual sense. There was no huge spiral galaxy filling the frame, no colourful nebula, and no bright planets surrounded by rings. The field contained many small galaxies scattered across a dark background. Near the centre was the thin feature, pointing away from a compact, slightly irregular galaxy. It looked almost as though someone had dragged a fine brush across the image. On closer inspection, the streak was not completely smooth. It contained brighter patches. Its narrow outer end included a compact bright spot, while the structure became somewhat wider as it approached the galaxy. The line also showed slight bends and variations rather than following a perfectly rigid path. That detail mattered. A detector defect often follows a pixel row or another regular direction inside the camera. A real astronomical structure can curve, broaden, and change brightness according to physical events taking place in space. The streak was bright enough to be measured clearly. Its total brightness was about 40% of the brightness of the galaxy to which it appeared connected. That is a surprising amount of light for something so narrow. It was not a faint thread visible only after extreme image processing. It contained a substantial population of luminous material. The galaxy and the streak also had nearly the same average colour in the original Hubble filters. That suggested they might be related, but colour alone was not enough to prove it. Objects at completely different distances can sometimes appear similar when their light is filtered through instruments and stretched by the expansion of the universe. A nearby blue star and a distant galaxy can produce measurements that look confusingly alike. Astronomy contains many examples of objects wearing similar colours while having nothing else in common. The universe has never shown much concern for making identification convenient. The team needed to determine whether the galaxy and the streak were actually at the same distance. For that, they used spectroscopy. A normal astronomical image records where light appears and how bright it is through one or more filters. A spectrum separates that light into its component wavelengths. Different atoms and molecules absorb or emit light at specific wavelengths, producing recognizable lines. Hydrogen has its own set of spectral lines. Oxygen has another. Nitrogen, sulfur, and other elements leave their own signatures. By studying these patterns, astronomers can learn what an object contains, how hot its gas is, what is causing the gas to glow, and how quickly the object is moving toward or away from us. Spectral lines also reveal redshift. As the universe expands, light travelling from a distant galaxy becomes stretched toward the longer wavelengths. If astronomers recognise a set of lines, but find that all of them have shifted by the same amount, they can calculate the object's redshift and estimate how far away it is. The team already had observing time scheduled at the Keck Observatory in Hawaii. They added the strange feature to the plan. Keck's low-resolution imaging spectrometer, usually shortened to LRS, was positioned so that its narrow slit covered both the compact galaxy and the long streak. Light from different points along the structure entered the instrument, allowing the team to compare the galaxy, the middle of the trail, and the bright region at its far end. The observations revealed several strong emission lines. They detected light associated with ionized oxygen, as well as lines produced by hydrogen. The The same lines appeared in both the galaxy and the streak at the same redshift. The connection was real. The redshift was measured at about 0.964. This meant the galaxy and the feature were being seen as they existed billions of years ago, when the universe was roughly half its present age. The apparently small line in the Hubble image was not small at all. Its projected length was about 62 kiloparsecs, which is approximately 200,000 light-years. The visible disk of the Milky Way is often described as being around 100,000 light-years across, although its more extended structures reach farther. The newly identified trail was roughly twice that familiar diameter. If the streak were placed across our own galaxy, one end could extend far beyond the region containing most of the Milky Way's stars. Yet in the Hubble photograph, it looked like a mark thin enough to be mistaken for damage to the image. Its great distance compressed an enormous physical structure into a very small angle on the sky. This is one of the practical difficulties of deep space astronomy. A single pixel may represent hundreds or thousands of light-years. Features that would dominate our entire night sky if they were nearby can become tiny smudges when observed from across the universe. The spectrum did more than establish distance. It showed that the trail was not uniform. The strength of the oxygen and hydrogen lines changed from one position to another. The gas also showed variations in velocity. Some parts behaved like regions where young stars were ionizing nearby hydrogen. Other parts had line ratios more consistent with fast shocks. Young massive stars produce large amounts of ultraviolet radiation. That radiation removes electrons from atoms in surrounding gas, causing the gas to glow. Astronomers can examine the relative brightness of several emission lines to determine whether this ionization is mainly being caused by stars, an active black hole, or a shock wave. A shock produces different temperatures and collision rates from those found in an ordinary star-forming cloud. Those conditions change how frequently particular atoms emit light. The result is a spectral pattern that acts as evidence of the physical process taking place. Along the mysterious line, the ratio of ionized oxygen to hydrogen changed dramatically. In some regions, it resembled normal star formation. In others, the oxygen emission was much stronger, pointing toward rapid shocks. At the narrow outer tip was an especially bright knot of ionized oxygen. This region was difficult to explain as an ordinary collection of stars. Something energetic appeared to be heating and compressing the gas there. The arrangement suggested a moving source. A fast object could create a strong shock at the front, while disturbed gas and newly formed stars remained behind it. Imagine pushing a spoon quickly through thick soup. Material builds up ahead of the spoon, while swirling patterns remain behind. The comparison is not exact, since intergalactic gas is considerably thinner than soup, and black holes rarely fit comfortably into kitchen utensils, but the basic idea is useful. A massive object moving faster than the local speed of sound produces a bow shock. Gas is compressed in front of it, flows around it, and enters a turbulent wake. If some of that gas can cool, dense regions may begin collapsing and forming stars. The Hubble image appeared to show the record of such a process. The bright, shocked region marked the leading end. The thin line behind it contained younger and older stellar populations created as the source moved along. The team studied the colours at different points along the streak. The pattern was not random. The stellar populations appeared to become older with increasing distance from the outer tip. That was exactly the arrangement expected if a moving object had triggered star formation behind it. The material closest to the active tip would have been disturbed most recently, so its stars should be younger. Material farther back would have been encountered earlier, giving its stars more time to age. Massive blue stars do not remain blue for very long by astronomical standards. They consume their fuel quickly, change colour as they evolve, and may explode after only a few million years. Their colours therefore provide rough information about when star formation occurred. By comparing the observed colours with models of stellar populations, the researchers could estimate an age sequence along the trail. The best-fitting early model suggested that the stars grew steadily older away from the tip. This did not prove that a black hole had made them. Several different events can create young stars in a line. The universe has plenty of ways to stretch, squeeze, and rearrange gas. The researchers had to examine other explanations. One possibility was a jet. Supermassive black holes near galactic centers can produce narrow jets of particles moving at almost the speed of light. These jets may extend for hundreds of thousands or even millions of light years. When they collide with gas, they can create bright knots and sometimes trigger star formation. A jet would naturally explain a long, narrow feature associated with a galaxy. It was therefore an important alternative. The problem was that the galaxy did not show the expected evidence of a powerful active nucleus. Its spectral lines were consistent mainly with ordinary star formation, rather than a bright active galactic nucleus. There was also no clear counterjet with the brightness and structure normally expected from a large bipolar outflow. The shape was unusual for a jet. The feature was narrow at the far end and broadened toward the galaxy, whereas many jets expand as they travel outward. Its light appeared to come largely from stars, not from the synchrotron radiation commonly produced by high-speed charged particles in a jet. A second possibility involved a tidal tail. When galaxies interact, gravity can pull long streams of stars and gas out of them. These tidal tails may stretch for enormous distances, and they can contain young stars formed from compressed gas. The irregular appearance of the compact galaxy suggested that it might have experienced a merger, so a tidal feature was reasonable. Yet tidal tails are usually broader, more irregular, and less astonishingly narrow. They often curve around the interacting galaxies rather than extending as a nearly straight line from a compact center to a sharp tip. The observed trail also had a velocity structure and shock pattern that did not fit comfortably with an ordinary tidal stream. Another explanation was gravitational lensing. A massive foreground object can bend the light of a more distant galaxy, stretching it into an arc. Some lensed galaxies appear as long, narrow streaks, particularly in images taken by Hubble. There was no suitable foreground mass in the correct position to produce this feature. The streak also connected physically to the compact galaxy at the same redshift. It was not simply the distorted image of an unrelated object behind a hidden lens. The line might have been an edge-on galaxy, viewed from the side so that its disk appeared extremely thin. Edge-on galaxies can resemble straight streaks, particularly when they are distant. An ordinary galaxy would be expected to have a central concentration of light and a more symmetric structure. This feature instead pointed directly from the compact galaxy and ended in an unusual bright knot. Its emission line properties changed along its length in a way that suggested shocks and sequential star formation rather than a stable rotating disk. The team also considered whether the line could be a chain of unrelated objects that happened to align by chance. Deep Hubble images contain large numbers of distant galaxies. Occasionally several can appear close together. The spectral observations made that explanation highly unlikely. The emission could be traced along the full length of the feature at the same redshift. This was one connected physical structure, not a fortunate queue of galaxies waiting patiently in the same direction. As the alternatives were tested, the runaway black hole interpretation became harder to ignore. A supermassive black hole could have been ejected from the galaxy during a merger involving other central black holes. After leaving the nucleus, it could travel rapidly through the surrounding circumgalactic medium. The circumgalactic medium is the thin reservoir of gas surrounding a galaxy. It extends far beyond the bright region containing most of the stars. This gas is extremely diffuse, but it contains a significant amount of matter and plays an important role in galactic growth. Gas can move from the surrounding medium into a galaxy, providing material for new stars. Winds and supernova can push matter in the opposite direction. The circumgalactic medium is therefore not empty space. It is a large, changing environment connecting a galaxy with the wider universe. A black hole travelling through that gas would focus some material gravitationally and drive a shock through the rest. The disturbed gas could cool and fragment in the wake. Young stars would then light the path after the black hole had moved on. The result could look much like the structure in the Hubble image. a narrow trail extending from the host galaxy, a sequence of star-forming regions, and a bright shock at the leading end. The trail was almost half as bright as the galaxy itself. That implied a large amount of recent star formation. It was not simply a few isolated stars scattered along the route. The wake contained enough young stars to become a major visible feature. A black hole normally reveals itself when matter falls toward it and becomes extremely hot. Here, the proposed black hole was not detected through a bright accretion disk. It was moving too quickly through gas that was too thin to produce the familiar appearance of a feeding quasar. Instead, its path was illuminated behind it. That makes RBH1 rather like an invisible aircraft detected only by its contrail. We do not see the aircraft directly, but the line shows its direction and recent movement. The comparison has limits, of course. An aircraft contrail is made when water vapour condenses behind an engine. The trail in this case contains newborn stars, which is a slightly more ambitious form of exhaust. The researchers also noticed a much fainter feature extending from the opposite side of the galaxy. It was shorter and harder to detect, but it appeared in ultraviolet light and showed a weak signal from ionized oxygen. The original interpretation suggested that the galaxy may once have contained 3 supermassive black holes. A chaotic 3-body interaction could have thrown one black hole in one direction and a binary pair in the other. Under that early scenario, the bright long wake would mark the path of the single runaway black hole. The fainter feature on the opposite side might show the path of the recoiling binary. The idea resembled a slingshot. When 3 massive objects interact gravitationally, energy can be redistributed among them. One may be accelerated outward, while the remaining pair moves in the opposite direction. The original study estimated that the main runaway object might have left the galaxy around 39 million years before the moment being observed. Combining the trail's length with the estimated stellar ages suggested a projected speed of roughly 1,600 kilometres per second. Later observations and modelling would revise the estimated speed and the likely ejection mechanism, but the first analysis already made one point clear. Whatever produced the trail was moving extraordinarily fast. At 1,600 kilometres per second, an object could travel around Earth in about 25 seconds, provided Earth kindly moved out of the way. Even the later estimate of close to 1,000 kilometres per second would still be enough to cross the distance from Earth to the Moon in only a few minutes. Those numbers are difficult to connect with a Hubble image because the trail itself appears completely still. We see the accumulated result of millions of years compressed into one observation. The black hole did not draw the entire line during the exposure. Hubble's camera collected light for a relatively short period. Each part of the streak was already glowing when that light began its journey toward us. The trail is a time record. The galaxy marks the starting region. The stars along the line formed at different stages. The bright outer tip shows the latest visible interaction between the moving object and the surrounding gas. Looking from the galaxy toward the tip is therefore similar to moving forward through the history of the ejection. The older evidence lies closer to the departure point. More recent evidence lies near the leading end. This makes the streak useful in a way that a single flash would not be. A brief explosion can reveal that something happened, but a long wake preserves information about an extended process. Its width, brightness, colours, gas velocities, and chemical emission all record different parts of the event. The line is not perfectly straight. Small deviations appear along its path. At first, that might seem to weaken the runaway interpretation. A fast black hole should travel along a smooth trajectory unless another large force changes its direction. The stars do not have to remain exactly on that trajectory after they form. Gas in the surrounding medium can move. Turbulence can push forming clouds sideways. The galaxy itself may have motion relative to the gas around it. The young stellar groups can drift after the black hole has passed. The small bends were therefore consistent with material being left behind in a changing environment. The black hole's path could remain comparatively direct, while the visible wake shifted around it. There was also a delay between the passage of the black hole and the appearance of bright stars. Shocked gas must cool, become dense, fragment, and collapse. A protostar then forms and begins nuclear fusion. The process is fast by galactic standards, but not immediate. The visible stars may have appeared thousands or millions of years after the black hole crossed their location. By then, the black hole had travelled far ahead. The trail did not mark its position at every instant with perfect accuracy. It showed where the consequences of its passage became visible. This helps explain why identifying the black hole itself was so difficult. The bright tip did not necessarily sit directly on the event horizon. The strongest shock, the compressed gas, and any stars forming nearby could be offset from the invisible object. Hubble could resolve the broad structure but not isolate a dark point inside the bright region. The black hole remained hidden among the effects it was producing. The discovery was announced in 2023 as a candidate runaway supermassive black hole. The word candidate mattered. The evidence was strong enough to make the idea serious, but not yet strong enough to treat every detail as settled. Science usually advances through stages like this. An unusual observation is reported. A physical explanation is proposed. Other researchers look for weaknesses, suggest alternatives, and request better data. A good hypothesis does not merely fit what has already been seen. It predicts what a more powerful observation should reveal. If a runaway black hole was moving supersonically at the tip, there should be a compact bow shock. Gas on different sides of that shock should show an abrupt change in velocity. The emission from oxygen, hydrogen, nitrogen, and sulfur should follow patterns associated with shock heating rather than ordinary star formation alone. The stellar ages should continue to support a moving source. Infrared observations should reveal whether dust-obscured structures were hiding inside the wake. The parent galaxy should show evidence of the violent merger required to eject a central black hole. These questions could not all be answered with the original Hubble image. Hubble had found the trail, but the line itself was only the beginning of the investigation. Even so, that first image changed the nature of the search. Astronomers had spent years trying to identify displaced supermassive black holes by looking for bright active nuclei outside galactic centres. RBH1 suggested another method. A quiet black hole might reveal itself by altering the gas it passes through. Instead of searching for light coming from matter falling into the black hole, astronomers could search for unusually long wakes of shocked gas and young stars. This method depends on circumstance. A runaway black hole crossing a region with little gas may leave no bright trail. One crossing dense material at the wrong temperature may heat the gas without creating stars. Another may move through a region hidden by dust. RBH1 appears to have crossed an environment that made its route visible. The gas was present, the shock was strong, and star formation occurred along an unusually narrow corridor. Hubble happened to observe the correct patch of sky, and an astronomer happened to notice a line that looked like an error. There may be other trails hiding in archival images. Some could have been classified as distant edge-on galaxies or image defects. Others may be too faint for current instruments. Finding them would require searching enormous collections of telescope data for a shape that astronomers did not know they needed to find until this one appeared. The thin blue streak had already provided several important clues. It connected physically to a compact star-forming galaxy. It extended for about 200,000 light-years. Its spectrum showed both young stars and fast shocks. Its stellar colours followed an age pattern consistent with a source moving away from the galaxy. At its outer end was a bright region where the gas appeared to be experiencing the most energetic disturbance. Those clues pointed toward an invisible object. That object is now called RBH1, and meeting it properly requires us to begin with an inconvenience. We cannot actually see the black hole. The bright knot at the front of the trail is not the black hole itself. The narrow line behind it is not light coming from inside the black hole, and the young stars are not material that escape from beyond its event horizon. What the telescopes record is the response of the surrounding gas. RBH1 remains dark while the environment around it provides nearly all the visible evidence. This is normal for black hole astronomy. A black hole does not have a solid surface that reflects sunlight, and light produced inside its event horizon cannot travel outward. Astronomers therefore find black holes by measuring their effects. They watch stars orbit invisible masses, detect hot gas falling inward, record gravitational waves from mergers, or observe matter being disturbed by an unseen source. RBH1 belongs to that last category. It has revealed itself by pushing gas out of the way. The letters in its name stand for runaway black hole, while the number 1 reflects its status as the first object of this particular confirmed kind. It is also described as a recoiling supermassive black hole because its motion was probably produced by a powerful gravitational recoil during an earlier merger. Runaway describes what it is doing now. Recoiling describes how it may have begun doing it. Neither term means the black hole is wandering without direction. Once it received its kick, it followed a path determined by its initial velocity and the gravity of the surrounding matter. Space provides no road signs, but it is very strict about momentum. The black hole is travelling at an inferred speed of about 954 kilometres per second. The uncertainty range places the likely value between roughly 830 and 1064 kilometres per second. Its path is tilted by about 29 degrees relative to the plane of the sky, which means astronomers are seeing a combination of motion across their view and motion along their line of sight. Those values came from modelling the sharp changes in gas velocity at the leading end of the wake. At the central estimate, RBH1 moves more than 82 million kilometres in a day. It could cover the average distance between Earth and the Moon in less than 7 minutes. It could travel a distance equal to Earth's orbit around the Sun in a little under 2 days. A journey from the Sun to Neptune would still take several weeks, which is a useful reminder that the solar system is large enough to make even a runaway supermassive black hole look briefly inconvenienced. The speed is extraordinary for such a massive object, although it is still far below the speed of light. RBH1 travels at about 0.3% of light speed. Light would cover the same distance more than 300 times faster. That difference matters because the black hole is not producing the extreme time dilation effects associated with fictional spacecraft moving close to light speed. Its unusual behaviour comes from the enormous amount of mass travelling through gas at a speed far greater than the local speed of sound. Sound in this setting does not mean something a human ear could hear. A sound wave is a pressure disturbance moving through a material, and even the extremely thin gas around a galaxy can transmit such disturbances. The speed of those waves depends mainly on the gas temperature and composition. RBH1 is moving through the circumgalactic medium faster than pressure changes can travel ahead of it. The gas receives very little warning. It cannot move aside gradually, so it becomes compressed into a shock. A similar effect forms around a supersonic aircraft, although the physical scale is completely different. An aircraft pushes through Earth's atmosphere and creates a cone-shaped disturbance. RBH1 pushes through gas spread across intergalactic distances and produces a curved bow shock at its leading edge. The black hole is not large in the ordinary sense. Its mass is enormous, but the region enclosed by its event horizon would be tiny compared with a 200,000 light-year trail. Current observations provide a lower mass estimate of about 10 million times the mass of the Sun. The true mass may be higher. The lower limit was derived by considering the energy needed to power the shock over the lifetime of the wake. A lighter object would have difficulty supplying enough mechanical energy to explain the observed disturbance while moving at the measured speed. 10 million suns represent an amount of matter that is difficult to picture. The Sun already contains more than 99% of the mass in our solar system. RBH1 contains at least 10 million solar masses concentrated into the compact region surrounding a black hole. That does not mean it has a gravitational pull equal to 10 million suns at every distance in some mysterious amplified form. From far away, gravity depends on mass and distance. If 10 million suns could somehow be gathered into one compact location, their distant gravitational influence would resemble that of a black hole with the same mass. The unusual feature is how closely matter can approach before reaching a physical surface, because there is no ordinary surface. As material moves inward, escape becomes increasingly difficult until it crosses the event horizon and can no longer return. A black hole of 10 million solar masses would have an event horizon scale measured in tens of millions of kilometres depending on its spin. That sounds large until it is compared with the wake. The visible trail is so much longer that comparing the event horizon with the wake is rather like comparing a grain of dust with a road extending across a continent, except the difference here is considerably greater, and the grain of dust can alter the motion of stars. The black hole's gravity affects gas near its root, but it does not pull in everything across the full width of the trail. Black holes are sometimes imagined as cosmic vacuum cleaners that drag in anything from a vast distance. If that were true, galaxies containing central black holes would not remain galaxies for very long. Matter must pass sufficiently close and lose enough energy to be captured. Gas farther away can be deflected, compressed, heated, and stirred without falling through the event horizon. Most of the visible wake consists of material that was affected by the black hole but not swallowed by it. RBH-1 may accrete some gas during its journey. The surrounding medium, however, is thin, and the black hole is moving through it very quickly. Material has little time to settle into a large, bright accretion disk. That helps explain why the black hole does not appear as a brilliant quasar at the trail's tip. A quasar forms when a supermassive black hole receives a large and sustained supply of gas. The material circles inward, becomes extremely hot through friction and compression, and produces enough radiation to outshine the surrounding galaxy. RBH-1 is crossing a sparse environment at high speed. It is closer to someone running through a light mist than someone sitting beneath a waterfall. A little material may be captured, but much of the gas is pushed, shocked, or left behind. The lack of a bright accretion source was one reason confirming the object was difficult. Hubble showed the trail, but not an obvious black hole. Astronomers needed a way to distinguish the wake of a massive travelling object from a jet, a tidal structure, or an unusual region of star formation. The James Webb Space Telescope supplied that test with its near-infrared spectrograph. Rather than taking only a normal picture, the instrument used an integral field unit to collect a spectrum at many positions across the tip of the wake. An ordinary spectrum may tell astronomers what is happening inside one narrow strip or aperture. Integral field spectroscopy produces a small data cube. 2 dimensions record positions on the sky, while the third records wavelength. Every part of the observed field receives its own spectrum. This allowed the team to map the movement and ionization of the gas around RBH-1's leading edge. Instead of seeing only a bright knot, they could compare one side of the knot with the other and examine how the gas changed across a region about 1 kiloparsec, or roughly 3,000 light-years, wide. Webb found a radial velocity change of approximately 600 kilometers per second across that region. Gas was being displaced rapidly around the front of an unseen moving source. Farther behind it, the shocked material had a projected flow speed of about 300 kilometers per second. Those measurements were not simply a faster part of the trail sitting beside a slower one. Their location and shape matched the expected flow around a bow shock. Gas meeting the front of the disturbance is compressed and redirected. It moves around the obstacle and enters the wake. The change in speed depends on the object's velocity, the shock angle, the compression of the gas, and the direction from which the system is being viewed. The researchers built a relatively simple geometric model of that flow. By matching the model to Webb's velocity map, they inferred the black hole's speed and the inclination of its path. The result was the estimate of roughly 954 kilometers per second. It was not obtained by watching the black hole move between 2 photographs. At such a great distance, its position would change far too little during a human lifetime for that method to work easily. Astronomers instead treated the gas as a speed-measuring instrument. The black hole pushed the material, and the material carried information about how quickly the pushing object was moving. This is rather like estimating the speed of a hidden boat by studying the size and direction of its wake. The boat itself might be concealed by fog, but the water still records its passage. With RBH1, the water is thin galactic gas, and the wake is long enough to contain generations of massive stars. The chemical fingerprint supported the same explanation. Webb measured emission from ionized oxygen, hydrogen, nitrogen, and sulfur. The relative strengths of those lines were consistent with fast radiative shocks, followed by rapid cooling. They were not well explained by ordinary ultraviolet light from young stars acting alone. A radiative shock occurs when gas is strongly heated by a shock, and then loses a significant amount of that energy as radiation. The gas entering the shock may reach very high temperatures. As it cools, electrons combine with ions or drop into lower energy states, releasing light at characteristic wavelengths. Different emission lines become strong under different conditions. Some respond to temperature, others respond to gas density, ionization, or the speed of the shock. Examining several of them together is more useful than relying on a single bright line. The measured line ratios produced shock speed estimates that agreed with the motion inferred from the gas geometry. Independent parts of the evidence were pointing toward the same physical event. That agreement is important. Almost any unusual object can be made to fit one isolated observation with enough creativity. A useful explanation must account for the shape, movement, temperature, and chemical behavior of the gas at the same time. The runaway model explains why there is a sharp feature at the tip, why gas is moving sideways at hundreds of kilometers per second, why the emission lines resemble fast shocks, why the wake extends back toward GX, and why young stars appear along the route. It also explains the change in velocity down the trail. Near the tip, the recently shocked gas moves rapidly relative to the surrounding medium. Farther back, its observed velocity falls from roughly 300 km per second to about 100 km per second near the former host galaxy. At first, that decline was puzzling. If the trail simply recorded gas thrown backward at one fixed speed, the movement should remain more uniform. The Webb study proposed that the shocked gas gradually mixes with the surrounding circumgalactic medium. Turbulence pulls additional material into the wake. As the moving gas incorporates more of the slower environment, its average velocity decreases. Later three-dimensional simulations examine this idea in greater detail. They found that radiative cooling and turbulent mixing could reproduce the coherent deceleration along the tail. When cooling was removed from the simulations, a long, organized cold tail did not form. The wake is therefore not a static scar, it is an active flow. Gas is compressed at the front, redirected around the bow shock, cooled, and mixed with its surroundings. Dense portions become unstable and begin forming stars. Farther downstream, the material slows and develops additional structure. RBH1 continues forward while these processes unfold behind it. At nearly 1,000 kilometers per second, the black hole travels about 1,000 parsecs in roughly 1 million years. By the time a compressed cloud completes the early stages of star formation, the black hole may already be several thousand light-years farther away. This separation prevents us from treating every bright stellar knot as the black hole's current location. The black hole should be near the leading shock, not inside the older star-forming regions downstream. The source is called a giant because of its mass, not because it occupies a large visible area. A black hole containing at least 10 million solar masses is classed as supermassive. It probably grew over a long period while it remained inside a galactic center. Supermassive black holes are not thought to begin at their final sizes. They gain mass by consuming gas and merging with other black holes. Their growth is connected with the development of the galaxies around them. RBH1's current isolation therefore hides a long earlier history. Before it became a runaway, it was probably a central black hole. Gas and stars moved around it. It may have experienced active periods when infalling material caused it to shine. It may also have spent long intervals accreting very little and remaining comparatively quiet. Then the conditions at the center changed. Another galaxy arrived with its own stars, gas, dark matter, and central black hole. Gravitational interactions altered both systems. The galactic structures merged over time, and the two central black holes were brought into the same nucleus. Current modelling suggests that the black hole merger responsible for RBH1 occurred about 70 million years before the stage captured in the observations. The progenitor black holes probably had a mass ratio no greater than about 6:1. The more massive member appears to have been spinning rapidly, with a dimensionless spin magnitude near 0.75, and the binary spins were likely misaligned enough for the orbit to precess. Those details are inferred rather than photographed. Astronomers cannot replay the merger. They work backward from the measured recoil speed and compare it with numerical models showing how different black hole masses and spins affect gravitational wave emission. A recoil near 950 kilometres per second requires a strongly asymmetric event. The waves leaving the merger must have carried more momentum in some directions than in others. The newly formed black hole received an opposing kick. A smaller recoil might have displaced it temporarily within GX. The black hole could have moved away from the centre, slowed under the galaxy's gravity, and eventually returned. RBH1 was kicked much harder. Its speed was sufficient to carry it tens of thousands of light years from the nucleus, and apparently beyond the galaxy's ability to bring it back. The black hole did not merely wobble around the centre, it escaped into the surrounding medium. This makes RBH1 important for more than its unusual trail. Physicists had predicted gravitational wave recoil long before observing a clear runaway object of this kind. Computer simulations showed that merging black holes could receive kicks ranging from modest velocities to several thousand kilometres per second, depending on their masses and spins. Finding RBH1 provides a physical system where those predictions can be tested against an actual measured wake. Its velocity contains information about a merger that happened tens of millions of years earlier. The trail is therefore doing two jobs. It records the black hole's movement through gas, and it provides indirect evidence about the black hole binary that existed before the recoil. The object may also help astronomers understand which supermassive black hole mergers will eventually be detected through gravitational waves. The progenitor analysis found that a similar event could produce an extremely strong signal for the planned Laser Interferometer Space Antenna, or LISA. Unlike ground-based detectors, LISA is designed to measure low-frequency gravitational waves in space and should be sensitive to mergers involving massive black holes. RBH1's original gravitational waves passed Earth billions of years ago and were not recorded. The light now reaching our telescopes shows the aftermath. Future observatories may detect both sides of similar events: gravitational waves during a merger and electromagnetic evidence from a displaced black hole afterward. For now, the object itself remains defined largely by lower limits and inferred values. Its mass is at least 10 million suns, but an exact mass has not been measured. Its velocity is close to 954 kilometres per second, with a range determined by uncertainties in the shock model. Its path is inclined relative to our view, but the complete three-dimensional environment is not known in perfect detail. The evidence is strong without being magically complete. Astronomy usually works that way. We receive limited light from a distant system, measure it as carefully as possible, and build an explanation that must satisfy every available constraint. RBH1 is not an ordinary black hole that happens to be in an unusual photograph. Its movement changes how it interacts with matter. A central black hole can sit within a rotating supply of gas for millions of years. A runaway black hole encounters new gas continuously and leaves the disturbed material behind before it can settle around it. That movement turns the object into a travelling source of shocks. It produces a narrow corridor where gas is heated, compressed, cooled, mixed, and sometimes converted into stars. The black hole has already moved roughly 62 projected kiloparsecs from GX. Correcting for the angle of its path makes the physical journey somewhat longer. Its estimated velocity and displacement are consistent with a travel time of around 70 million years, close to the inferred time since the progenitor merger. During those 70 million years, many species have appeared and vanished on Earth. Continents have shifted. Climate has changed. The black hole, meanwhile, has continued along one enormous path, covering a distance comparable to the size of a large galaxy. Its trail has not formed at a constant brightness. Gas density changes from place to place. Some regions respond strongly and form many stars. Others remain faint. The wake widens and slows as turbulent material mixes with its surroundings. RBH1 itself continues to lead the structure. It does not turn around to inspect the work. The stars behind it are consequences, not companions. There may be matter travelling very close to the black hole, perhaps gas or stars that remained gravitationally bound during the kick. The existing observations do not provide a clear inventory of such material. The dominant visible feature is the much larger disturbed environment. Any compact cluster carried with the black hole would be difficult to separate from the bright shocked region at this distance. Future observations may improve the limits, but the current identification does not depend on seeing a group of stars orbiting RBH1. It depends on dynamics. A massive object is moving supersonically. The gas velocity changes abruptly around its leading edge. The emission lines match rapid shocks and cooling. The required energy implies a mass in the supermassive range. A 200,000 light-year wake points back toward a galaxy capable of having contained such an object. Taken together, those measurements introduce RBH1 more clearly than any direct portrait could. It is an invisible body with at least 10 million solar masses, travelling near 1,000 kilometres per second, driving a bow shock through circumgalactic gas, and leaving a cooling, star-forming flow behind it. That description tells us what RBH1 is doing. It does not yet explain why GX once contained the conditions needed to launch it. A gravitational wave kick of this strength requires a particular kind of black hole merger, and that merger almost certainly began with a much larger collision between galaxies. To understand how the runaway giant left home, we need to return to the period before the trail, when GX had not yet settled into its compact shape, and two galactic systems were bringing their central black holes toward the same crowded centre. The same crowded centre brings us to a name that has become attached to this story in several popular accounts: the cosmic owl. It is an excellent name for an astronomical object. It is memorable, easy to picture, and far more appealing than the catalogue numbers astronomers usually receive. Unfortunately, the name does not belong to RBH1's former home. The actual galaxy connected to the runaway black hole is called GX. It is a compact, star-forming galaxy at a redshift of about 0.96. The cosmic owl is a different system at a redshift of 1.14, found in another part of the sky. Both involve colliding galaxies, active supermassive black holes, compressed gas, shocks, and unusually intense star formation. Those similarities have led to some understandable confusion, especially when several discoveries involving both systems appeared within a short period. So RBH1 did not fly out between the two bright eyes of the cosmic owl. GX and the cosmic owl are separate objects. The owl is still useful here because it gives us a much clearer view of the kind of galactic collision that may once have transformed GX. One system shows us a merger while its separate galaxies and black holes are still visible. The other may show us what can happen much later, after the galaxies have combined and their black holes have completed a far more dangerous meeting. The cosmic owl was identified in deep observations of the cosmos field. It consists of two colliding galaxies with remarkably similar ring-shaped structures. Their compact central regions appear as two bright eyes, while a blue area of intense star formation between them resembles a small beak. The resemblance is good enough that even astronomers, who can usually be relied upon to name things with strings of letters and numbers, accepted that this one looked like an owl. Each ring is about 8 kiloparsecs across, or approximately 26,000 light-years. The two central cores are separated by a similar distance. Both galaxies contain older stars inside their rings, and younger, bluer stars around the outside. The rings were probably produced by a nearly head-on collision. A normal spiral galaxy contains stars, gas, dust, and dark matter arranged in a rotating disk. When another galaxy passes close by, gravity pulls on every part of that disk. When the second galaxy passes directly through it, the disturbance can move outward as a large density wave. The stars do not all fly away. Many of them continue orbiting while their paths become rearranged. Gas behaves less politely. Gas clouds collide, compress, heat, and lose energy. An outward moving wave can gather gas into a broad ring where new stars begin to form. The process is sometimes compared with ripples spreading across a pond after a stone falls into it. That comparison is useful as long as we remember that the pond is tens of thousands of light years wide. The stone is another galaxy, and the ripple may produce billions of stars. It would be a difficult pond to maintain. Most galaxy collisions do not create such neat rings. The path must be reasonably direct, and the orientations of the galactic disks have to cooperate. A glancing encounter produces a different result. It may stretch long tidal tails from the galaxies, distort spiral arms, and pull streams of gas across hundreds of thousands of light years. A head-on passage drives a disturbance through the disk more symmetrically. The original center can remain visible while material moves outward into a ring. The cosmic owl is especially unusual because both galaxies have ring structures of similar size. This suggests that they were relatively similar before the collision. A very small galaxy passing through a much larger one might create a ring in the larger disk while suffering a less organized fate itself. In the owl, each participant appears to have received a substantial and almost matching disturbance. The combined stellar mass of the system is estimated at about 320 billion times the mass of the Sun. That is not the total mass, because it does not include all of the dark matter and gas, but it shows that this is a collision between two large galaxies rather than one large galaxy inconvenienced by a minor satellite. Astronomers call an interaction between galaxies of similar mass a major merger. A major merger can change nearly every large-scale property of the galaxies involved. Their shapes can be destroyed or rebuilt. Their gas can be driven inward or thrown outward. Their rates of star formation may rise sharply. Their central black holes may begin feeding more actively. Even the directions in which their stars orbit can be reorganized. A minor merger, involving a large galaxy and a much smaller companion, can still produce important changes. The Milky Way has absorbed smaller systems throughout its history and continues interacting with satellite galaxies. A major merger, however, affects both participants so strongly that neither can continue as though nothing happened. The cosmic owl gives us a visible example of this disruption. Between its two bright central regions lies the blue beak. This area contains a large reservoir of cold gas and an intense burst of star formation. Gas from the two galaxies has met at the collision front. The clouds do not pass through each other as easily as most stars do. They collide, become compressed, and create dense regions where gravity can form new stars. Both eyes of the owl also contain active galactic nuclei. An active galactic nucleus forms when a central supermassive black hole is consuming enough material to produce a bright accretion flow. The black hole remains dark, but the gas surrounding it becomes extremely hot and luminous. One of the owl's active nuclei produces a bipolar radio jet. The jet extends toward the region between the galaxies and appears to strike the merging front. That gives the gas an additional source of pressure and shock heating. The starburst in the beak may therefore be receiving help from two directions. The galaxy collision compresses the gas as the systems meet, while the black hole jet adds another shock. Under the right conditions, those disturbances can increase the density of cold material and encourage it to collapse into stars. This is closely related to what appears to be happening behind RBH1. In both cases, a shock acts on gas and helps produce star formation. The source of the shock is different. In the cosmic owl, gas from two galaxies collides, and a jet from one of the central black holes may strike the same region. In the RBH1 system, the black hole itself moves through the gas and creates a bow shock. The result is not identical, but the underlying lesson is similar. Gas does not care whether compression arrives from a supernova, a galaxy collision, a radio jet, or a runaway black hole. It responds to pressure, temperature, motion, gravity, and its ability to cool. A strong shock can prevent star formation if it heats the gas too much, or drives it out of the galaxy. The same shock can promote star formation if the compressed material radiates away its heat and becomes dense enough to collapse. This is why black hole feedback is sometimes described as positive and sometimes as negative. Positive feedback increases star formation. Negative feedback reduces it. The labels do not mean that the black hole is behaving well or badly. They describe the effect on the rate of star formation. Black holes have no performance review and appear comfortable with that arrangement. The cosmic owl lets astronomers observe both active black holes before the galaxies have fully combined. GX is seen at a later and less obvious point in a merger history. Recent modelling of RBH1 suggests that GX was probably created in a major, gas-rich merger between galaxies of comparable mass. The inferred mass ratio is no greater than about 4:1. That means the smaller participant may have contained at least a quarter of the mass of the larger one, rather than being a tiny satellite. A gas-rich merger is often called a wet merger. The term is informal but useful. It means the galaxies contain large supplies of cold gas capable of forming stars and feeding black holes. A dry merger involves galaxies with relatively little cold gas. Their existing stars combine, but the encounter may produce less new star formation. The galaxies are not literally wet or dry. No astronomer is required to test them with a towel. GX appears to have formed through the wet variety. The strong star formation in GX supports the presence of gas, while the long wake behind RBH1 shows that substantial material also existed around the galaxy. A gas-rich environment would have helped the two original galaxies lose orbital energy and bring their central black holes together. To understand that process, imagine two galaxies beginning far apart. Each contains hundreds of billions of stars, or perhaps fewer, depending on its size. Each also sits inside a much larger halo of dark matter. At the centre of each galaxy is a supermassive black hole. The galaxies approach because their total gravitational pull changes their motion. They may begin on an elongated orbit, pass one another, move apart again, and then return. During the first close passage, their shapes become distorted. Long tidal tails can form as gravity pulls stars and gas outward. Bridges of matter may connect the two systems. Gas clouds collide and lose energy, while star formation increases in compressed regions. The galaxies do not usually merge during that first encounter. They may separate by tens or hundreds of thousands of light years before falling together again. Their second passage is slower and often more disruptive. Orbital energy has been transferred to surrounding stars, gas, and dark matter. The galaxies move closer, their structures overlap more strongly, and their central regions begin sinking toward a shared centre. This loss of orbital energy is partly caused by dynamical friction. Despite the name, dynamical friction is not the same as rubbing two surfaces together. A massive object moving through a field of stars and dark matter pulls surrounding material gravitationally. That interaction creates a slight concentration of matter behind it. The concentration then pulls backward on the moving object, reducing its speed. The lost orbital energy is transferred to the surrounding system. A galaxy moving through another galaxy's dark matter halo experiences this effect. Its orbit gradually shrinks. The same process later affects the supermassive black holes as they move through the combined stellar environment. Gas makes the merger even more efficient because gas can collide and radiate energy away. Stars mostly pass one another without direct contact. Gas clouds cannot ignore one another so easily. When gas streams meet, they produce shocks. The gas heats, emits radiation, and settles into new orbits. Some is driven toward the centre by gravitational torques created during the collision. Those torques occur because the merging galaxies are no longer perfectly symmetric. Bars, tidal arms, and other distortions pull on the gas and remove angular momentum. Angular momentum is what normally allows material to orbit instead of falling straight inward. Reduce enough of it, and the gas moves toward the centre. This inward flow can trigger a central starburst. It can also supply fuel to one or both supermassive black holes. A black hole that had previously been quiet may become active as fresh gas reaches its surroundings. The material forms an accretion disk, heats up, and emits radiation. Winds and jets may emerge, carrying energy back into the galaxy. For a while, the merging system can contain two active galactic nuclei, just as the cosmic owl does now. Each black hole still belongs to its original galactic core, even though the wider stellar structures have begun overlapping. The two nuclei may be separated by tens of thousands of light years. Over time, dynamical friction brings them closer. At large distances, the black holes do not orbit each other directly. Each one is carried inside a dense collection of stars and gas left from its original galaxy. Those compact cores move within the new merged system. As their separation decreases, tidal forces strip stars and gas from the cores. The black holes become more exposed. Eventually, they are close enough for their mutual gravity to dominate their movement. At that point, they form a bound binary. The path from two separate galaxies to a binary supermassive black hole is long. It can take hundreds of millions of years, and the details depend on the masses, gas content, orbital geometry, and internal structure of the galaxies. A nearly head-on collision like the cosmic owl can create dramatic rings. An off-center merger may create tidal tails and a highly distorted remnant. A collision between disks moving in the same direction can evolve differently from one involving opposing rotations. There is no single standard appearance for a major merger. Galaxies are not manufactured with convenient alignment marks. GX is compact in the observations we have. The evidence does not allow astronomers to reconstruct a detailed photograph of the original galaxies before they collided. The properties inferred from RBH1's recoil do provide constraints. The two original supermassive black holes could not have had an extreme difference in mass. Current calculations suggest a black hole mass ratio no larger than about 6:1. Because the masses of central black holes tend to relate roughly to the properties of their host galaxies, the researchers used that result to infer a galaxy mass ratio no larger than around 4:1. This points toward a major merger rather than a small galaxy being absorbed by a much larger one. The original galaxies were probably rich in gas because gas helps solve an important problem. Once two supermassive black holes become a binary, they must continue losing energy before they can merge. At first, nearby stars interact with the binary. A star passing close to the black holes can gain energy and be thrown outward. The binary loses a corresponding amount of energy and becomes tighter. This process works well while many stars pass through the central region. Eventually, however, the binary may remove most of the stars on useful orbits. The supply can become depleted. If nothing replaces those stars, the black holes may stop shrinking at a separation of roughly a parsec. A parsec is about 3.26 light years. This difficulty is known as the final parsec problem. A separation of a few light years sounds small compared with the size of a galaxy. It is still too large for gravitational wave emission to bring many supermassive black hole binaries together within the age of the universe. Something must help the black holes cross that remaining distance. Gas can provide one solution. A dense disk around the binary can exchange angular momentum with the black holes and shrink their orbit. Irregular stellar motion inside a merger remnant can continually send new stars near the centre. A third black hole can also disturb the system, although the latest modelling of RBH1 does not require the original three black hole slingshot explanation. The inferred wet merger in GX would have provided plenty of gas and a highly disturbed central environment. Both conditions can help a binary overcome the final parsec problem. This is where the cosmic owl becomes a useful comparison again. Its galaxies are still visibly separate. Its two black holes remain inside the bright eyes. Gas is being compressed between them, and at least one jet is interacting with the collision front. The system shows how a merger can activate black holes, redistribute gas, and create a large starburst before the central objects have joined. GEX may once have gone through a broadly similar stage, though not necessarily with twin rings or an owl-like shape. Two gas-rich galaxies approached. Their stars and dark matter halos interacted. Gas lost energy and moved inward. Their central black holes became active or remained hidden behind dust. The galaxies passed through one another, separated, returned, and gradually combined. Over time, the original structures became difficult to recognize. Spiral arms were stretched or destroyed. Gas collected in the center or was pushed outward. New stars formed in bursts. The two galactic nuclei moved closer until the black holes inside them formed a binary. The merger remnant may have looked chaotic during that period. Dense gas clouds would have surrounded the central region. Stars would have followed a wide variety of orbits. The black holes would not have been sitting quietly at the middle of a smooth, settled galaxy. That chaos was useful. It supplied repeated gravitational interactions and gas torques that removed energy from the binary. As the separation decreased, the black holes orbited faster. A pair separated by thousands of light years might require millions of years to complete an orbit. At a separation of only a few light years, the orbital period could fall to years or decades depending on the masses. Closer still, the speeds became a significant fraction of the speed of light. The binary's gravity stirred nearby gas. If enough material remained, it could form a larger disk around both black holes, with smaller flows feeding each member. The changing gravitational field might create gaps, streams, shocks, and periodic variations in brightness. From far away, the system could have appeared as a single active galactic nucleus, even though two black holes were hidden inside it. Resolving a binary at such a small separation in a distant galaxy would be beyond the ability of ordinary telescope images. The two objects would continue losing orbital energy through interactions with matter. Once they became sufficiently close, another process began to dominate. Accelerating masses disturb space-time. A pair of massive black holes orbiting rapidly produces gravitational waves. Those waves carry energy and angular momentum away from the binary. At first, the loss is slow. The black holes complete many orbits while moving inward gradually. As their separation shrinks, the gravitational wave emission becomes stronger. The orbit tightens more quickly. The black holes move faster, producing stronger waves, which remove energy even more efficiently. The final approach begins to accelerate. By then, the original galaxies have already completed most of their merger. The two black holes are no longer the separate eyes of a system like the cosmic owl. They are an extremely compact binary buried inside the center of one remnant galaxy. The moment when the two black holes became one was not a collision in the familiar sense. There were no solid surfaces to strike, no crusts to crack, and no pieces of either black hole scattered into space. Each object was a region enclosed by an event horizon. During the final approach, those horizons moved through a rapidly changing gravitational field until a single, common horizon formed around both of them. Long before that happened, the binary had already lost most of the distance that once separated the two galactic centers. Stars, gas, and dark matter had helped bring the black holes together. Once the separation became small enough, gravitational waves took over as the main way the system lost energy. The two black holes orbited a shared center of mass. Their motion continuously changed the shape of the surrounding gravitational field. Those changes travelled outward as gravitational waves carrying energy and angular momentum away from the binary. As energy left, the orbit became smaller. A smaller orbit made the black holes move faster. Faster movement produced stronger gravitational waves which removed energy more quickly. The process accelerated itself. This stage is called the inspiral. The name is straightforward. The objects spiral inward while their orbital speed and gravitational wave frequency increase. For most of the inspiral, the orbit could still be described as a sequence of slowly shrinking loops. The black holes completed many revolutions, losing a small portion of their remaining orbital energy during each one. Their separation decreased gradually rather than collapsing all at once. Near the end, gradual stopped being a useful description. The black holes entered a region where space-time was strongly curved by both masses at once. The orbit tightened rapidly, and the system moved from inspiral into a plunge. Numerical relativity simulations describe the full event as an inspiral, followed by a rapid plunge and merger, and then a ring down of the newly formed remnant. It may be tempting to picture the black holes as two dark spheres circling each other. That image is useful at a distance, but it becomes less accurate during the final moments. An event horizon is not a material shell. It is a boundary determined by the structure of space-time and by which paths can still lead outward. The geometry around each black hole was also affected by its spin. A rotating black hole drags nearby space-time around with it. This effect is called frame dragging. If the spin axis had pointed in the same direction as the orbital angular momentum, the motion would have been more orderly. The orbital plane would have remained comparatively stable, and the strongest gravitational wave pattern would have possessed more symmetry. RBH1's progenitors were probably not arranged that neatly. The measured recoil of the final black hole suggests that the binary was precessing. At least one spin was tilted relative to the orbital axis, and the more massive black hole likely had a dimensionless spin magnitude of about 0.75. The inferred mass ratio was no more extreme than roughly 6:1. Those conditions allowed the orientation of the binary to change as the objects approached each other. Precession is similar to the wobbling motion of a spinning top, although the black holes were not moving through a room or leaning under ordinary gravity. Their spins interacted with the orbital motion and with each other through the curved geometry around them. The direction of the orbital plane shifted. The spin axes changed their orientation. From a fixed location far away, the gravitational wave signal would have varied as the system turned and wobbled. This motion mattered greatly for what happened after the merger. A symmetric binary tends to emit gravitational waves in a more balanced way. A precessing binary with unequal masses and misaligned spins can send different amounts of gravitational wave momentum in different directions. Before reaching that imbalance, it helps to understand what an observer would have detected during the approach. Gravitational waves stretch and compress distances by an extremely small amount as they pass. A detector does not hear them as ordinary sound. It measures changes in the separation between freely moving objects. The signal from a binary inspiral is often described as a chirp because its frequency and amplitude rise toward the merger. A recording shifted into the range of human hearing would begin with slower cycles and become faster and louder. For a supermassive binary, the natural gravitational wave frequencies are much lower than those produced by the stellar mass black hole mergers measured by ground-based instruments. The enormous masses make the orbital timescales longer. A future space-based detector, such as LISA, is being designed for this lower frequency region. The RBH1 progenitor analysis found that similar mergers could produce exceptionally strong LISA signals, with estimated signal-to-noise ratios exceeding 1,000 in favourable cases. The original event occurred far too long ago to have been recorded by a human instrument, but a comparable merger in the future could be observed in detail through its gravitational waves. Such an observation could begin well before the final merger. Astronomers might follow the inspiral as the orbital frequency slowly increased. The waveform would reveal information about the masses, spins, orientation, and distance of the system. The signal would not provide a normal picture. It would be closer to receiving the changing rhythm of the gravitational field and reconstructing the source from that rhythm. Mass affects how quickly the signal evolves. Unequal masses alter its harmonics. Spin changes the orbital dynamics. Precession adds modulations as the system changes orientation. The waveform is therefore not just an announcement that two black holes exist, it is a detailed record of how they move. In the case of RBH1, astronomers have been forced to work backward. They did not measure the original waveform, they measured the speed of the remnant tens of millions of years later, and used numerical models to infer which kinds of binary could have produced it. The exact masses of the two progenitor black holes remain uncertain. The remnant has a lower estimated mass of about 10 million suns, so the original pair together must have contained at least a similar amount before part of their total energy was radiated away. The black holes did not simply add their measured masses together and preserve every kilogram inside the remnant. Some of the system's mass energy left as gravitational radiation. Einstein's relation between mass and energy applies here in a direct way. The energy carried by gravitational waves reduces the final mass of the merged black hole compared with the total mass energy of the original binary. The exact fraction depends on the mass ratio and spins. Numerical relativity calculations show that black hole mergers can radiate several percent of the initial mass energy, while particular rapidly spinning configurations can radiate more. The details for RBH1's progenitors cannot be reconstructed precisely from the wake alone. Even a few percent of a supermassive binary's mass represents an extraordinary quantity of energy. Suppose, only as a simple illustration, that the binary contained 10 million solar masses in total and radiated 3% during its complete evolution. That would correspond to the mass energy of roughly 300,000 suns, leaving primarily as gravitational waves. It would not appear as a conventional flash in the sky. Gravitational waves interact very weakly with matter. They could cross stars, planets, gas clouds, and entire galaxies without depositing much of their energy. This makes them difficult to detect, but it also allows them to preserve information from regions that light cannot escape or pass through easily. Any gas surrounding the binary might have produced electromagnetic radiation of its own. A merger inside a dense galactic nucleus could disturb an accretion disk, change the flow of material, or alter the activity of the central source. The observations of RBH1 do not tell us exactly how bright that earlier galactic center became. The parent merger was gas-rich, so material was probably present, but the amount and arrangement of gas close to the final binary remain unknown. The gravitational merger itself did not require gas. Once the black holes reached the stage where gravitational wave emission dominated, the binary could complete its inward spiral even if the immediate region around it had become relatively empty. This point separates the cause of the merger from any light that may have accompanied it. The black holes merged because their orbital energy and angular momentum were carried away. Nearby gas could respond, but it did not need to act as glue during the last stage. As the separation fell, the distinction between two individual black holes became increasingly difficult to maintain. Each horizon was distorted by the companion. The surrounding gravitational field changed rapidly and became strongly nonlinear. Nonlinear means that the combined gravitational field could not be found by simply calculating each black hole separately and adding the two results together. Einstein's equations allow gravity itself to affect the way gravity evolves. Near the merger, the interactions become too strong for simple approximations. This is why numerical relativity is necessary. Researchers represent space-time on powerful computers and solve Einstein's equations step by step. The calculation must follow the horizons, the gravitational waves, and the changing geometry without producing artificial instabilities. Early attempts to simulate full black hole mergers were extremely difficult. The coordinates used to describe space-time could stretch or fail. Small numerical errors could grow. The singular regions inside the black holes required careful treatment. Successful simulations eventually show that the binary passes smoothly from in spiral to plunge, forms a common horizon, and settles into one rotating black hole. These simulations also allow researchers to calculate the energy, angular momentum, and linear momentum carried away by the waves. The formation of the common horizon can be considered the central merger event. Before it forms, two separate event horizons exist. Afterward, one connected horizon surrounds the remnant. That does not mean the new black hole is immediately calm. The first common horizon is strongly distorted. It has inherited mass and angular momentum from both members of the binary, but the distribution of the surrounding curvature has not yet settled into a stable form. The remnant behaves somewhat like a bell that has been struck, provided the bell is made from curved space-time, has no solid material, and is not something one should attempt to hang in a church tower. The distorted black hole emits additional gravitational waves. These waves carry away the remaining irregularities. The signal becomes a combination of damped oscillations known as quasi-normal modes. This stage is called ring down. Each mode has a characteristic frequency and decay time, determined mainly by the final black hole's mass and spin. Measuring several modes in a future gravitational wave event could allow physicists to test whether the remnant behaves as general relativity predicts. The oscillations fade because energy is carried away by gravitational waves and absorbed by the horizon. The black hole settles toward the stable rotating solution described by the Kerr geometry. Ring-down studies use those characteristic oscillations to infer the properties of the remnant. For RBH1, the ring-down would have ended very quickly compared with the 70 million years of travel that followed. The black hole would have become a stable rotating remnant, long before it produced most of the visible trail. The object moving through the circumgalactic gas today is not still vibrating violently from the merger. It is a settled black hole carrying the mass, spin, and velocity left by that event. Its spin is the result of several contributions. Both progenitor black holes had their own rotations. The binary also possessed orbital angular momentum because the black holes were circling one another. Some angular momentum escaped in gravitational waves. Much of the remainder became the spin of the final black hole. The final spin cannot exceed the physical limit for a Kerr black hole. If too much angular momentum were concentrated relative to the mass, the expected event horizon structure would not be maintained. The merger radiates enough energy and angular momentum to leave a physically allowed remnant. The process does not require anyone to apply a brake. The gravitational waves provide the accounting. The final black hole's mass is lower than the total mass energy available before the merger. Its spin differs from either progenitor spin. Its direction of motion may also differ dramatically from the motion of the original binary centre of mass. That last property brings us back to RBH, one's departure from GX. Before the merger, the two black holes orbited around a common centre. The binary as a whole probably remained near the centre of the merged galaxy. Gas, stars, and dark matter surrounded it. After the common horizon formed and the ring down faded, the remnant was moving at nearly 1,000 kilometres per second. The central question is how a system that began close to the galactic centre ended with its only remaining black hole travelling fast enough to escape. Ordinary orbital motion cannot explain it by itself. During the merger, the individual black holes may have moved at enormous speeds, but their motions were largely opposite. If the entire process had been perfectly symmetric, the final black hole would have remained near the original centre of mass. Imagine two identical skaters moving toward each other with equal speeds. If they meet and hold on, their opposing momentum cancels. The combined pair remains close to the meeting point. A black hole merger is much more complicated, but conservation of momentum still applies. Something had to carry momentum in one direction for the remnant to move in the other. That something was the gravitational radiation. Gravitational waves do not merely carry energy, they carry angular momentum and linear momentum as well. If equal amounts of linear momentum leave in every direction, the net effect on the remnant is zero. The merger that produced RBH1 was not so balanced. The black holes probably had unequal masses. Their spins were misaligned. The orbital plane was precessing. During each stage of the inspiral and merger, the strength and direction of the radiation pattern changed. A more massive black hole does not move around the shared centre in the same way as a lighter companion. A spinning black hole distorts the surrounding geometry differently depending on the direction and magnitude of its spin. When the spins tilt out of the orbital plane, the whole system develops additional asymmetries. Numerical simulations show that unequal masses alone can produce a recoil, even when neither black hole spins. For non-spinning binaries, calculations found maximum kicks of around 175 kilometres per second for particular unequal mass ratios. That would be enough to move a remnant away from the centre of a small galaxy, and could eject it from some dwarf systems. It is not enough to explain RBH1's inferred velocity. Spin can increase the recoil considerably. When the black hole spins point in different directions, gravitational wave emission above the orbital plane can differ from emission below it. Radiation may also become uneven within the plane. The resulting recoil depends sensitively on the spin orientations at the moment of merger. Two binaries with the same masses and the same spin magnitudes can produce different kicks if their spins point in different directions. The merger phase at which those spins line up relative to the orbit also matters. This sensitivity is one reason astronomers cannot recover one perfectly unique history for RBH1. Several progenitor configurations can produce a recoil near the measured speed. The recent analysis narrows the possibilities. It indicates that a non-processing binary is unlikely to have delivered the required kick. The more massive black hole probably had a relatively high spin, and the mass ratio could not have been extremely unequal. These constraints describe the binary shortly before it merged, not the appearance of the galaxies during their first collision. The gas-rich major merger created the environment. The Longin spiral shaped the binary. The final orbits determined the gravitational wave pattern. Most of the recoil accumulated near the merger, when the radiation was strongest. The black hole did not spend millions of years gradually accelerating to its final runaway speed. During the Longin spiral, small amounts of momentum could be carried away over many orbits. Because the source rotated, contributions from different directions often cancelled. Near the final plunge, the gravitational waves became much stronger, and the rapidly changing geometry produced a large burst of momentum. Ring-down radiation added its own contribution after the common horizon formed. In some configurations, the direction of the momentum flow can change during ring-down and partly reduce the earlier kick. This is known as an anti-kick. The final velocity is the sum of the entire gravitational wave history, rather than one isolated push. For RBH1, the completed accounting left the remnant moving at close to 1,000 kilometers per second. The black hole received no engine, expelled no propellant, and collided with no hidden object. Space-time itself carried momentum away from the merger. For a brief period, the galaxy's centre contained one of the most energetic events possible. Two supermassive black holes completed their final orbit, formed a common horizon, radiated part of their mass energy, and settled into a single rotating remnant. The centre did not remain quiet afterward. The gravitational waves left at the speed of light, spreading through the universe. The new black hole moved in the opposite response to their uneven momentum. Within a short time, it had crossed the dense central region that had once held both progenitors. Stars and gas nearby experienced a sudden change. The binary they had orbited was gone. One black hole remained, its mass slightly reduced by gravitational radiation, and its trajectory no longer centered on the galaxy. The remnant traveled outward through the merger debris, then into the thinner gas surrounding GX. The dense center fell behind. The galaxy had completed a major merger, and almost immediately by astronomical standards, lost the supermassive black hole produced by it. To send such a massive object away at RBH1's speed, the gravitational radiation had to be remarkably uneven, and the direction of that unevenness had to remain coherent through the most violent part of the merger. Most of the momentum that launched the new black hole was carried away during the final moments of the merger, when the gravitational waves were strongest and the geometry around the binary was changing most rapidly. Before those moments, The two black holes had spent a long time circling one another. Their radiation pattern rotated with the orbit, so a stronger pulse emitted in one direction could be partly balanced by another pulse emitted elsewhere during a later orbit. As the black holes entered their final plunge, there was no longer enough time for every contribution to cancel. One side of the system released more gravitational wave momentum than the other. The waves travelled away at the speed of light. The newly formed black hole moved in the opposite direction. This was the gravitational kick. The word kick makes the event sound as though something struck the black hole from outside. Nothing did. There was no passing star, hidden explosion, or enormous cosmic boot waiting near the centre of GX. The recoil came from the merger itself. Gravitational waves carry linear momentum as well as energy and angular momentum. When their emission is uneven, conservation of momentum requires the remaining object to move in the opposite direction. Numerical relativity models predict that generic mergers involving unequal masses and misaligned spins can produce recoil speeds of thousands of kilometres per second. Extreme configurations may approach 5,000 kilometres per second, although most mergers are expected to produce much smaller kicks. A useful comparison can be made with a person standing on a smooth frozen lake and throwing a heavy bag. The bag moves one way and the person slides the other way. The total momentum remains balanced. In a black hole merger, the object being thrown is not a bag or any ordinary matter. It is an uneven pattern of gravitational radiation spreading outward through space-time. The merged black hole slides in the opposite direction with enough speed to move across a galaxy. The comparison becomes less helpful if we imagine the black hole gradually accelerating over a long distance. The strongest recoil was delivered very near the merger. RBH1 did not begin moving slowly and then spend millions of years building speed. It emerged from the final merger already travelling rapidly relative to the centre of GX. Its inferred speed is about 954 kilometres per second, with an estimated uncertainty of minus 126 and plus 110 kilometres per second. Modelling indicates that the black hole's path is inclined by about 29 degrees relative to the plane of the sky. That velocity is not the maximum allowed by general relativity, but it's far too large to be explained by unequal masses alone if the black holes were not spinning. Simulations of non-spinning black holes show that unequal masses can create recoil because the smaller black hole moves more rapidly around the common centre and produces different radiation pattern from the larger one. The largest kick expected from this mass asymmetry alone is about 175 kilometres per second. RBH1 is moving more than 5 times faster than that. Spin must therefore have played a major role. A rotating black hole changes the geometry around it. When two spinning black holes orbit each other, the direction and strength of their gravitational wave emission depend on the orientation of those spins relative to the orbit. If both spins are aligned with the orbital axis, much of the system remains symmetric above and below the orbital plane. The resulting recoil can still be significant, especially if the masses differ, but producing a kick near 1,000 kilometers per second becomes difficult. If the spins are tilted, the binary begins to precess. The orbital plane and spin directions change as the black holes approach. The gravitational wave pattern becomes more complicated and less balanced. Recent analysis of RBH1 found that its progenitor binary was probably precessing. The mass ratio between the two black holes was likely no greater than about 6:1, and the more massive black hole probably had a dimensionless spin near 0.75. A spin of 0 would describe a non-rotating black hole, while a value approaching 1 represents extremely rapid rotation. A spin near 0.75 is not a minor rotation. It means the larger black hole carried substantial angular momentum into the merger. The direction of that spin also mattered. A rapidly spinning black hole with its axis aligned neatly with the orbit would not produce the same recoil as one tilted across the orbital plane. The kick depends on the full arrangement. The two masses, both spin magnitudes, both spin directions, the orbital orientation, and the phase of the binary at merger. This dependence makes the process extremely sensitive. Two black hole binaries can contain the same masses and the same spin strengths, but produce different final velocities because their spins point in different directions. In one configuration, the waves may nearly balance and leave the remnant moving at only a few tens of kilometers per second. In another, the same basic ingredients can combine to produce a kick capable of ejecting the remnant from a galaxy. The original black holes in GX did not arrange themselves for the purpose of producing RBH1. Their spins were shaped by their earlier histories. A black hole can gain spin by consuming gas that repeatedly orbits in the same direction. It can also have its spin changed by previous mergers. Gas flowing coherently toward a black hole may gradually align its rotation with the surrounding disk, while chaotic episodes of accretion can feed it from different directions and leave the spin tilted. The major merger that formed GX would have disturbed the gas around both central black holes. Dense streams could have arrived from changing directions. The black holes may have entered the final binary with spins that were never fully aligned. Gas sometimes helps align black hole spins before a merger, which can reduce the chance of a large recoil. That alignment is not guaranteed. It depends on the amount of gas, the structure of the accretion flow, the masses of the black holes, and how much time remains before they merge. In GX, enough misalignment apparently survived to make the binary precess and release gravitational waves unevenly. The result was a recoil large enough to remove the new black hole from the central region. This does not mean the entire galaxy was physically thrown in the opposite direction at nearly 1,000 kilometers per second. The black hole represented only a small fraction of the galaxy's total mass. Conservation of momentum applied to the complete system, but the motion distributed through the galaxy would have been extremely small compared with the speed of RBH1. The gravitational waves also did not strike the stars like a blast wave. They passed outward with very weak direct interaction. Even though they carried an enormous amount of energy, they stretched and compressed local distances by only tiny fractions as they travelled through matter. The galaxy was disturbed mainly because its central black hole suddenly began moving away. A supermassive black hole normally rests close to the lowest point in a galaxy's gravitational potential. It does not hold the whole galaxy together. Stars far from the centre orbit according to the combined gravity of stars, gas, dark matter, and the central black hole. Removing the black hole would not cause the galaxy to fly apart. In most regions, the gravity of the larger galaxy dominates. Near the nucleus, however, the black hole can be the most important individual mass. Stars may orbit it closely. Gas may form a disk around it. Its radiation and outflows may regulate the temperature and movement of material in the central region. When RBH1 received its kick, all of those relationships changed. Some matter very close to the black hole could remain gravitationally bound and travel with it. Whether an object stayed attached depended on its orbital speed and its distance from the black hole before the recoil. Imagine a group of passengers standing on a platform that suddenly accelerates. Those standing close to a strong support may move with it. Those farther away are left behind. The real calculation involves gravity rather than handrails, but the idea is similar. A star orbiting very near the black hole might have been moving fast enough to remain bound after the kick. A more distant star could find that the centre of its orbit had abruptly departed. Its new path would then be controlled by the remaining galaxy. The same applies to gas. The innermost part of an accretion disk could have accompanied RBH1, while material farther out remained near the centre of GX or was thrown onto a new orbit. Models of recoiling supermassive black holes predict that a compact disk and a tightly bound cluster of stars can travel with the remnant. Such a black hole might remain visible for a while as an active galactic nucleus displaced from the galactic centre. The length of that activity depends on how much gas remained bound and how quickly it was consumed. RBH1 does not currently appear as a bright displaced quasar. Any compact fuel supply carried from the nucleus may have been limited. Consumed long ago, or too faint to separate from the shocked region around the black hole. The object has been travelling for roughly 70 million years. Even a substantial accretion disk would have difficulty sustaining bright quasar activity for that entire journey without receiving new material. The black hole can collect a small amount of gas as it moves, but its speed works against efficient feeding. Gas approaching RBH1 is strongly deflected and shocked. Only material passing sufficiently close with suitable motion can lose enough energy to become bound. Most of the gas does not settle into a stable disk. It moves around the black hole and enters the wake. The immediate effect inside GX would have been much more dramatic than the quiet appearance of the present trail suggests. The remnant black hole formed near the centre, received its recoil, and began crossing the dense nuclear environment. It may have passed through gas clouds, star clusters, and debris left by the galactic merger. At nearly 1,000 kilometres per second, it could cross a central region 1,000 light-years wide in about 300,000 years. That is a short interval compared with the lifetime of a galaxy, although it remains considerably longer than the time normally allocated for leaving a building after an alarm. As RBH1 moved outward, the galaxy's gravity pulled backward on it. The black hole did not travel through empty space at a perfectly constant speed. It climbed out of the gravitational potential of GX, converting some of its kinetic energy into gravitational potential energy. If the initial kick had been lower than the escape velocity, RBH1 would have slowed, stopped at some maximum distance and fallen back. It might then have passed repeatedly through the galactic centre on a long orbit. Interactions with stars, gas and dark matter would gradually remove energy from its motion. Over millions or billions of years, it could settle back into the nucleus. Simulations show that black holes receiving moderate kicks can oscillate around galactic centres for long periods. Kicks close to the escape speed can send them tens or hundreds of kiloparsecs away and keep them displaced for more than 1 billion years before returning. A stronger kick allows the black hole to escape entirely. Escape velocity is not one universal number for every galaxy. It depends on the galaxy's mass distribution and on the position from which the object begins. A dense, massive galaxy has a deeper gravitational potential and requires a higher escape speed than a small diffuse galaxy. Dark matter also matters. Even after a black hole leaves the bright stellar body, it may remain inside a much larger dark matter halo. Escaping the visible galaxy is easier than escaping the entire halo. Current studies describe RBH1 as likely ejected from GX, and its long outward trail strongly supports that interpretation. The exact mass distribution of GX is not known well enough to provide a perfectly measured escape velocity, so astronomers infer the outcome from the observed displacement, speed, travel time, and properties of the galaxy. At minimum, RBH1 has travelled far beyond the compact visible body of its former host. It is now moving through the circumgalactic environment rather than remaining near the nucleus. If it is fully unbound, it will continue into intergalactic space and never return to GX. The galaxy's central black hole will then remain absent unless another black hole later arrives through a merger or a new massive seed somehow forms and grows near the centre. That absence can affect the future development of the galaxy. Supermassive black holes and their host galaxies grow together over long periods. Gas falling toward the central black hole can produce radiation, winds, and jets. Those outflows can heat or remove gas and regulate star formation. Without a central black hole, GX may experience less black hole feedback in its nucleus. Gas that might otherwise have fed an active galactic nucleus could remain available for star formation, be expelled by stellar activity, or settle into other structures. The effect is not simple enough to predict from the recoil alone. GX still contains stars, supernovae, gas pressure, magnetic fields, and perhaps smaller black holes. Those processes continue to shape it. The missing supermassive black hole removes one important influence, but it does not leave the galaxy inactive. The ejection also changes the familiar relationship between a galaxy's central bulge and its black hole mass. In many galaxies, larger stellar bulges tend to contain more massive central black holes. GX may retain the stellar system produced by its major merger, while losing the black hole associated with it. A survey conducted much later could therefore find a compact galaxy with an unusually small central black hole mass, or no detectable central supermassive black hole at all. Gravitational recoils may contribute to the scatter in observed relationships between black holes and galaxies. They may be especially important in smaller galaxies, where escape velocities are lower and central black holes are easier to remove. Simulations also suggest that repeated recoil events can reduce the fraction of low-mass galaxies retaining central black holes. The departure itself can alter the distribution of stars near the centre. Before the merger, the binary black holes may already have removed stars from the nucleus through gravitational interactions. Stars passing close to the binary could gain energy and be thrown onto wider orbits, creating a lower density core. A recoiling remnant can add to that effect. If the black hole remains bound and repeatedly crosses the centre, it transfers energy to surrounding stars and enlarges the core. Recent simulations find that strong but bound recoils can increase core sizes and stellar mass deficits substantially. RBH1 may have crossed the central region only once before escaping, so its effect would differ from a black hole making repeated passages. Even one rapid departure could disturb nearby orbits and carry away matter that had been tightly attached to the centre. The phrase "shook a galaxy" therefore does not describe one uniform vibration passing through every star. The galaxy experienced several connected changes. Gravitational waves removed energy and momentum from the binary. The merged black hole recoiled. Stars and gas that had orbited the binary suddenly faced a different central mass distribution. Some matter travelled with the black hole, other material was left behind. The nucleus lost a source of gravity, accretion and feedback. The galaxy had spent hundreds of millions of years bringing two central black holes together, only to lose the final object almost immediately after they merged. There is a slight administrative unfairness in this. GX completed the difficult work of combining two galaxies, driving gas inward, overcoming the final parsec problem, and delivering both black holes to the point of merger. The remnant then left before contributing much to the settled galaxy that followed. Nature does not provide compensation for this sort of thing. The direction of the kick was also important. RBH1 travelled outward along the line now traced by young stars. Had the recoil pointed through a region containing less gas, the black hole might still have escaped but left a much fainter wake. Had it moved through a dense galactic disk rather than out toward the halo, it might have accreted more strongly, produced a brighter active source, or generated a wider and more chaotic disturbance. The observed line reflects both the black hole's velocity and the environment selected by the kick direction. That direction was determined during the last stages of the merger. Small differences in the spin orientations could have launched the remnant elsewhere. The long stellar trail therefore preserves the result of an event that occurred on scales smaller than a solar system, but affected a region larger than the Milky Way. This contrast is common in black hole physics. The decisive interactions happen close to the event horizons, where the black holes are separated by distances tiny compared with their host galaxy. The consequences then spread outward through gravitational waves, displaced gas, moving stars, and the path of the remnant. As RBH1 crossed the nuclear region, it probably began producing a shock almost immediately. The central gas was dense, turbulent, and already disturbed by the galaxy merger. Any early wake may have mixed with that environment and become difficult to distinguish. Farther from GX, the surrounding gas became thinner and more uniform. The black hole's motion then began drawing the narrow, recognizable line found by Hubble. The wake did not appear all at once. RBH1 travelled onward while the shocked gas behind it cooled. Dense regions collapsed. Young stars turned on and made the black hole's earlier route visible. The distance between GX and the present tip is about 62 kiloparsecs in projection. Correcting for the inferred inclination increases the actual distance travelled. A speed near 954 kilometres per second over roughly 70 million years is consistent with a journey of that scale. During every second of that journey, RBH1 covered almost 1,000 kilometres. It travelled more than 30 billion kilometres in a year. In 1 million years, it crossed roughly 3,000 light-years. The galaxy behind it became steadily smaller, while the black hole entered gas that had never before passed close to a supermassive object. Its gravitational kick was over. No continuing force was pushing it forward. Momentum now carried the remnant through the outer environment of GX, while the galaxy's gravity and the resistance of the thin gas made comparatively small changes to its motion. The black hole had become a projectile with at least 10 million solar masses. Ahead of it, circumgalactic gas remained quiet and diffuse. At the moment RBH1 reached each new region, that gas was compressed into a bow shock. Behind the shock, it cooled, mixed, and began producing the line of stars. It did not slow enough to lose the trail behind it. Once the merged black hole had escaped the crowded centre of GX, it continued outward at close to 1,000 kilometres per second, carrying no engine, releasing no exhaust, and receiving no further push from the event that launched it. The gravitational kick had lasted only briefly. The journey that followed continued for tens of millions of years. RBH1's inferred velocity is about 954 kilometres per second. The uncertainty in the measurements allows a somewhat lower or higher value, but the central estimate is useful for understanding the scale of its motion. In 1 second, the black hole crosses nearly 1,000 kilometres. In 1 minute, it travels more than 57,000 kilometres. During a single hour, it covers about 3.5 million kilometres. A full day carries it more than 82 million kilometres farther from where it began. Those distances sound enormous, and they are, but the trail behind RBH1 is larger still. The visible feature extends about 62 kiloparsecs across the sky, which corresponds to roughly 200,000 light-years. Webb's measurements indicate that the path is inclined by about 29 degrees relative to the plane of the sky, so the actual route is probably somewhat longer than the length we see projected in the image. Simple geometry places it near 70 kiloparsecs, although the precise value depends on the shape of the path and the surrounding environment. At its measured speed, RBH1 travels a little more than 3,000 light-years during 1 million years. Covering the inferred distance therefore requires around 70 million years, which agrees well with independent modelling of the black hole merger that probably launched it. This agreement matters. Astronomers did not simply choose a travel time that made the story convenient. The distance, velocity, viewing angle, and recoil models all lead toward approximately the same period. The two black holes merged around 70 million years before the stage recorded by our telescopes. The resulting remnant then travelled outward, while its wake developed behind it. Measurements made from two very different parts of the problem, one involving galactic distances and another involving gravitational wave recoil calculations, fit together. 70 million years is a long time for anything living on Earth. It is short compared with the life of a galaxy. When RBH1 began its journey, the galaxy it left behind was still settling after a major merger. Stars formed during that collision were aging. Gas was cooling, collapsing, or being driven into new regions. The compact remnant called GX continued to evolve while its central black hole moved farther away. RBH1 did not remain close enough to watch those changes in any meaningful sense. It crossed thousands of light-years every million years and entered increasingly thin gas outside the bright body of the galaxy. The route was not empty. Images of space often show black backgrounds between stars and galaxies, creating the impression of a perfect vacuum. Intergalactic space is extremely sparse, but it contains gas, plasma, magnetic fields, radiation, dust, and dark matter. Around a galaxy lies a particularly important region known as the circumgalactic medium. It can extend far beyond the visible collection of stars. Much of its gas is hot and thin, making it difficult to see directly, but it contains a significant part of a galaxy's ordinary matter. The circumgalactic medium supplies galaxies with fresh material. Gas can cool and move inward, eventually contributing to new stars. Supernovae and active black holes can send gas outward, where it mixes with material already surrounding the galaxy. This region is not a quiet border separating a galaxy from nothing. It is an active exchange zone. RBH1 travelled directly through it. From our point of view, the black hole moves forward through stationary or slowly moving gas. From the black hole's point of view, the situation is reversed. A stream of material approaches from the front at nearly 1,000 kilometres per second. Both descriptions are valid. Motion has to be measured relative to something. The black hole does not feel a conventional wind. There is no atmosphere pressing against a solid surface, because the black hole has no solid surface. Gas approaching the event horizon does not bounce away as it would from the front of an aircraft. Most of the surrounding gas never reaches the event horizon. It passes at a much greater distance, where gravity bends its path and the collective pressure of the gas produces a shock. The motion is supersonic. This means RBH1 moves faster than pressure disturbances can travel through the surrounding medium. Gas ahead of a slowly moving object can begin responding before the object arrives. Pressure waves move outward and give the material time to shift gradually. When an object outruns those waves, the gas cannot adjust smoothly. Material gathers into a sharp compression region. On Earth, a supersonic aircraft produces a shock wave because information about its approach cannot travel through the air quickly enough. Pressure changes accumulate into a narrow front. An observer may hear the resulting sonic boom after the aircraft has already passed overhead. No human ear could hear the shock around RBH1. The gas is far too thin, the scale is far too large, and there is no atmosphere carrying sound toward us. The underlying physics still involves a disturbance moving faster than the local speed of sound. Webb detected the result through the motion and emission of the gas. Across a region roughly 1 kiloparsec wide at the leading tip, the radial velocity changes by about 600 kilometers per second. Behind the shock, gas has a projected motion near 300 kilometers per second. A bow shock model reproduces that pattern when the hidden source moves at about 954 kilometers per second. A kiloparsec is about 3,260 light-years. The sudden change in velocity therefore occurs across a region larger than many collections of stars, even though it appears compact in Webb's distant view. RBH1 itself is vastly smaller than this disturbed area. The black hole's event horizon may span tens of millions of kilometers, depending on its true mass and spin. The shock it produces extends across thousands of light-years because it is not simply the physical outline of the black hole. It is a large response created in the gas. A small boat can produce a wake much wider than the boat. A fast aircraft can disturb an area much larger than its fuselage. RBH1 creates an even more extreme separation between the size of the moving object and the size of its influence. Its gravity begins redirecting matter before that matter comes close to the event horizon. Gas particles moving toward the black hole are pulled inward. Their paths converge behind it, and interactions within the gas convert organized movement into heat, pressure, and turbulence. Individual stars would mostly pass without colliding with anything. Gas cannot behave in quite the same way because its particles interact and transmit pressure. When streams of gas are focused into the same region, they collide, heat, and change direction. Some material may be captured by the black hole. Most of it is not. The high speed of RBH1 makes feeding inefficient. A gas cloud has only a short time to respond before the black hole passes. To become bound, material must move close enough and lose sufficient energy. Gas farther away is disturbed but remains outside. This helps explain why RBH1 is not surrounded by a brilliant accretion disk. A slowly moving black hole inside a dense galactic center may collect a large supply of gas. That gas can orbit, lose angular momentum, heat up, and produce an active galactic nucleus. RBH1 crosses sparse material too rapidly for most of it to settle. The black hole is therefore visible mainly through the gas it fails to consume. That is a useful reversal of the normal black hole story. Astronomers often detect a black hole by watching matter disappear inward. Here, they detect one by watching matter remain outside, become compressed, and light up after the black hole has passed. The wake is not smoke released by RBH1. It is not a jet fired backward to propel the black hole forward. It is surrounding material that has been processed by the passage. A boat leaves water behind because the boat moves through water that was already present. An aircraft contrail forms because the aircraft changes conditions in the surrounding air. RBH1 leaves a stellar trail because it changes conditions in gas that already occupied the space around GX. The trail does not move as one rigid object with the black hole. Each region remains approximately where it formed, although the gas and stars have their own local motions. The black hole continues forward, and newer sections of the wake appear closer to its current position. The portion near GX was produced earlier. The section near the leading tip is younger. The visible structure is therefore arranged partly by time. Looking along it from the former host toward RBH1 is similar to examining later stages of the journey. This is not a perfect clock. Gas takes time to cool. Stars do not begin shining at the exact instant the shock passes. Turbulence moves material sideways, and different regions can collapse at different rates. The overall age pattern still follows the movement of the black hole. The original Hubble analysis found that the stellar colours were consistent with populations becoming older, farther from the leading tip. That was one of the first pieces of evidence that a source had moved along the structure while triggering star formation behind it. At nearly 1,000 kilometres per second, RBH1 crosses 1 light-year in a little over 300 years. That may sound slow after hearing the velocity in kilometres per second. Light crosses the same distance in 1 year, so the black hole requires more than 3 centuries. Space is large enough to make an object moving millions of kilometres per hour appear gradual. A person watching from nearby would not see RBH1 streak across the sky like a meteor. There would be no glowing black sphere rushing past with stars emerging immediately behind it. The surroundings would change over timescales far longer than a human life. The black hole would take thousands of years to cross even a modest part of the visible shock region. A cloud compressed today might not form bright stars until RBH1 had moved far beyond it. The Hubble image combines these slow developments into one narrow feature because it shows many locations at once. The full trail contains the accumulated results of tens of millions of years. RBH1's movement is rapid when measured against galactic gravity, but slow when measured against the enormous distances involved. This difference also affects our ability to watch it directly. Even though the black hole travels a remarkable distance every year, the system is so far away that its angular position changes by an extremely small amount on our sky. Astronomers cannot simply take another photograph next year and watch the tip leap forward. The motion must be inferred from the disturbed gas, the stellar age pattern, the length of the wake, and the recoil calculations. The gas becomes our substitute for a speedometer. Its velocity reveals the strength of the encounter. Its emission lines reveal how strongly it was heated. Its cooling behaviour explains why part of the wake remains coherent rather than dispersing immediately. The trailing gas does not keep moving at one fixed speed. Webb found that the observed radial velocity decreases from roughly 300 kilometres per second near the tip to about 100 kilometres per second closer to GX. This originally seemed difficult to explain. A simple stream launched behind a moving object might be expected to preserve a more uniform motion. Later simulations showed that radiative cooling and turbulent mixing can naturally produce the observed decline. Shocked gas mixes with the slower circumgalactic medium. As additional material is drawn into the wake, the combined flow decelerates. Without efficient cooling, the simulations do not produce the same long, coherent cold tail. The slowing gas should not be confused with the speed of the black hole. The wake loses speed relative to its surroundings as it mixes. RBH1 continues ahead at close to the inferred recoil velocity, subject to the gravity of the galaxy and its wider halo. Gas resistance can exert some drag on a massive moving object, but the circumgalactic medium is extremely thin. Over the observed journey, the black hole has retained enough speed to reach its present position. A person placing a hand outside a moving car feels a strong push because Earth's atmosphere is dense. RBH1 crosses a medium containing very few particles in each unit of volume. The black hole's gravity affects those particles over a large region, but there are not enough of them to stop a 10 million solar mass object quickly. Its momentum is enormous. Momentum is mass multiplied by velocity. A grain of dust moving rapidly can carry very little momentum because its mass is tiny. A freight train moving more slowly carries far more. RBH1 combines supermassive mass with extreme speed. Stopping or sharply redirecting it would require a major gravitational encounter. An ordinary star or gas cloud could not do so. Even a large star cluster would have little effect unless the passage were extremely close. The wider gravity of GX has the greatest continuing influence. As the black hole climbs outward, the galaxy pulls backward. Whether RBH1 has fully escaped the entire dark matter halo depends on the halo's mass and the exact three-dimensional velocity, but it has clearly travelled far beyond the compact stellar body. Its path through the gas appears relatively straight because no large object has passed close enough to bend it strongly. Small changes may still occur, and the visible wake can shift because the gas has its own motion. This helps explain why the trail is not a perfectly ruled line. The black hole may follow a smooth trajectory while the material behind it drifts. Circumgalactic gas can contain currents, temperature differences, turbulence, and density variations. A star-forming knot may inherit sideways motion from the cloud in which it developed. The wake can therefore bend slightly without requiring RBH1 to zigzag through space. A supermassive black hole would be difficult to make zigzag. There are no steering controls, and the nearest massive objects are separated by large distances. Once launched, it follows the combined result of momentum and gravity. The density variations in the gas also explain changes in brightness along the trail. When RBH1 enters a denser region, more material passes through the shock. The compressed wake can cool more effectively and produce more stars. In a thinner region, the trail may become faint. The black hole's speed remains similar while the environment changes around it. This is why the wake should not be treated as a simple line drawn with uniform ink. Each section records different local conditions. Some parts contain strong emission from ionized oxygen. Others are dominated by light from young stars. The width and velocity also change with distance. Together, those changes allow astronomers to study not only the black hole, but the otherwise difficult to see gas surrounding GX. RBH1 acts as a moving probe. A medical scan can reveal hidden structures by passing energy through a body and recording the response. The runaway black hole does something loosely comparable on a galactic scale. Its passage disturbs material that would otherwise remain faint, and that disturbance allows astronomers to measure the gas. This was certainly not the purpose of the gravitational recoil. The universe does not appear to have designed RBH1 as an instrument. It has nevertheless become a useful one. The shock reveals where gas is present. The cooling wake provides information about density and temperature. The deceleration measures how the shocked material mixes with the surrounding medium. The stars reveal where compression became strong enough to produce gravitational collapse. Every part of the trail is connected to movement. Without the recoil, the black hole would have remained in GX. Without its high velocity, it would not create the same bow shock. Without the surrounding gas, the route would remain invisible. Without rapid cooling, the wake would disperse before forming a narrow line. Several conditions had to occur together. The original merger needed to generate a recoil close to 1,000 kilometres per second. The kick had to point through a gas-rich part of the circumgalactic medium. The gas had to respond through shocks and cooling. Hubble then had to observe the field from an angle that made the long trail recognisable. A different viewing direction might have hidden much of the length. If RBH1 were travelling almost directly toward or away from Earth, the wake would appear greatly shortened because most of it would lie along our line of sight. The velocity would show up more strongly in the spectrum, but the long blue streak might not appear in the image. The actual inclination gives astronomers both kinds of evidence. Much of the trail stretches across the sky, while part of the motion occurs along our line of sight and changes the measured wavelengths of the emission lines. This combination allowed Webb to reconstruct the geometry. Gas moving toward us shifts spectral lines slightly toward shorter wavelengths. Gas moving away shifts them toward longer wavelengths. By mapping these changes across the bow shock and wake, astronomers can estimate the three-dimensional direction of the flow. The black hole's present motion is not measured by light emitted from the black hole itself. It is reconstructed from the movement of gas on either side of an invisible source. There is something practical about that method. Astronomers do not require the object to cooperate. They need only enough surrounding material to reveal what it is doing. RBH1 has already crossed a distance comparable with the diameter of a large galaxy. If it remains unbound, the journey may continue for billions of years. The wake will not remain bright for that entire period. Massive blue stars will age and die. Gas will disperse. Stellar groups may separate and become part of the wider intergalactic population. New sections could form ahead if the black hole continues to encounter suitable gas. A long empty region might interrupt the trail. A denser cloud could produce a brighter concentration. What we see is one period in a much longer route. The image does not tell us where RBH1 will eventually go. It may remain associated with the extended halo of GX for a long time, or it may travel into the space between galaxies. Gravity from nearby structures will slowly alter its path. No future destination is required for the present explanation. The measured trail shows that the black hole has already travelled far enough and fast enough to produce a unique record of its escape. The most important activity takes place at the front. There, gas that has remained undisturbed for millions or billions of years suddenly meets a moving gravitational source with at least 10 million times the mass of the Sun. Pressure cannot carry warning ahead quickly enough. The material is compressed, heated, and redirected around the invisible object. The temperature rises first. Star formation does not begin inside the hottest part of the shock. Gas that is too hot has enough internal motion to resist gravitational collapse. The material must lose energy. Atoms and ions release radiation. Cooler gas becomes denser. Turbulent layers mix hot and cold material. Small irregularities grow into larger concentrations. RBH1 continues onward while those changes occur behind it. The object associated with destruction does not gently place stars into the wake. It creates a violent compression front, and the ordinary behaviour of cooling gas does the rest. At the curved leading edge, the flow separates around the black hole's path. Farther behind, pressure falls, cooling becomes efficient, and material begins gathering into the dense structures from which the first new stars can emerge. Those dense structures do not appear immediately. At the front of the wake, the gas first experiences conditions that seem more likely to prevent star formation than encourage it. The material is struck, compressed, heated, and forced to move around the path of RBH1. Temperatures rise, atoms lose electrons, different streams of gas begin colliding and mixing. Only after the disturbed material has travelled farther downstream can enough heat escape for some regions to become cold and dense. The bow shock begins that process. A bow shock forms when an object moves through a medium faster than pressure waves can travel ahead of it. The name comes from the curved wave that forms in front of the bow of a ship. A similar shape appears around a fast aircraft and around stars moving supersonically through interstellar gas. RBH1 creates a version thousands of light years across. The black hole does not have a hull pushing directly against the gas. Its event horizon is far smaller than the visible shock, and most of the surrounding material never approaches it. The disturbance forms because the black hole's gravity redirects gas across a much larger region. Material passing on either side is pulled inward, while gas closer to the path is focused more strongly. Those converging flows cannot simply pass through one another. Gas particles collide, transfer energy, and create pressure. Their organised motion becomes heat and turbulence. At the leading edge, the surrounding gas meets this disturbance abruptly. The pressure, temperature, density, and velocity change over a relatively narrow region. That sudden transition is what astronomers call a shock front. The word front may suggest a flat wall, but the shape is curved. Gas reaches the centre of the bow almost head-on. Material entering farther from the central path meets the shock at an angle and is directed around the sides. Webb's observations reveal this geometry through the movement of the gas. Across a region about 1 kiloparsec wide at the tip of the trail, the measured radial velocity changes by approximately 600 kilometres per second. A kiloparsec is more than 3,000 light-years. The sharpest visible part of the disturbance is therefore larger than many small galaxies, even though it appears as a tiny knot in the telescope data. The gas does not make a complete 600 km per second turn in a single ordinary cloud. Astronomers are comparing different regions around the curved shock. One side contains material with a larger component of motion toward us, while another contains material moving more strongly away from us. By combining that velocity pattern with the flow observed behind the shock, researchers reconstructed the speed and orientation of the hidden source. Their model found that RBH1 is moving at about 954 km per second along a path inclined roughly 29 degrees from the plane of the sky. The shape and motion agree with what should happen around a supersonic object. The gas is compressed at the front, redirected around the disturbance, and carried into the wake. Spectroscopy provided another part of the evidence. The glowing gas contains hydrogen, oxygen, nitrogen, and sulfur. These elements emit light at particular wavelengths after their electrons have been removed, excited, or returned to lower energy states. Astronomers measured lines including hydrogen alpha, ionized oxygen, ionized nitrogen, and several forms of ionized sulfur. The brightness of one line compared with another depends on the conditions inside the gas. Young stars can create strong emission lines by releasing ultraviolet radiation. An active black hole can produce a different pattern. Fast shocks create another set of ratios because collisions heat the gas and strip electrons from atoms in a characteristic way. No single line provides a complete answer. Hydrogen may glow in a star-forming cloud, a shock, or gas near an active galactic nucleus. The useful information comes from comparing several lines. At the tip of RBH1's wake, the combined ratios match fast radiative shocks followed by rapid cooling. The shock speeds inferred from those ratios agree with the speeds expected from the black hole's motion and the curved geometry of the bow. This agreement is difficult to produce accidentally. The image shows the correct shape. The velocity map shows the correct motion. The chemical emission shows the correct heating and cooling conditions. The gas is being struck by something massive and supersonic. Calling the surrounding material sleeping gas is convenient, although the gas was not completely inactive before RBH1 arrived. Its particles moved continuously. The material had a temperature, pressure, and internal turbulence. Gravity from GX and its dark matter halo affected it. Radiation from stars and galaxies passed through it. What the gas lacked was sufficient density to form stars efficiently. A thin cloud can contain an enormous total mass, while remaining too spread out to collapse. Gravity pulls every particle toward every other particle, but thermal motion and pressure push against that attraction. Turbulence and magnetic fields may provide additional support. For a cloud to form stars, gravity must overcome those opposing effects in at least some regions. RBH1 changes the balance by compressing the gas. When material enters the bow shock, particles are forced closer together. The density rises. In a simple, strong shock that cannot cool quickly, the density may increase by a limited factor. If the shocked material can radiate away its heat, much greater compression becomes possible. Cooling reduces pressure. With less pressure resisting compression, the gas can contract further. A region that was previously too diffuse to collapse may become dense enough for its own gravity to take control. The first stage remains extremely hot. A shock produced by motion near 1,000 kilometres per second can heat gas to temperatures of millions of degrees, depending on how directly the material meets the shock and how its energy is distributed. Gas at such a temperature will not immediately form a star. Its particles move rapidly, and the resulting pressure works against collapse. The heat has to leave. Atoms and ions in the gas provide a way for that to happen. Collisions raise electrons into higher energy states. When the electrons fall back, they release photons. Those photons travel away, carrying energy with them. The emission lines detected by Webb are part of that cooling process. Hydrogen contributes. Oxygen, nitrogen, sulfur, and other heavier elements can be especially effective because their electrons have many available energy transitions. Each transition releases light at a particular wavelength. This means the same glowing lines that allow astronomers to identify the shock are also evidence that the gas is losing the heat deposited by it. The process does not happen at one fixed temperature. Gas immediately behind the shock may be highly ionized and extremely hot. As it cools, different ions become common and different emission lines grow stronger. Farther downstream, hydrogen begins recombining. Cooler phases develop. Molecules may eventually survive or form in the densest protected regions, allowing the temperature to fall much lower. Dust, when present, can also help. It shields parts of the gas from radiation and provides surfaces on which molecular hydrogen can form. The exact dust content of every part of RBH1's wake has not yet been mapped, but the parent system was already chemically enriched enough to contain elements heavier than helium. This is not pristine gas left untouched since the early universe. Previous generations of stars had produced and distributed heavier elements before the black hole arrived. Cooling alone does not guarantee collapse. The gas must remain concentrated for long enough. If turbulence tears a cloud apart too quickly, the material will disperse. If external pressure falls suddenly, it may expand again. If radiation from nearby massive stars becomes too intense, it can heat or ionize the cloud. The wake contains many competing processes. The shock compresses gas, which promotes collapse. The shock also creates heat and turbulence, which can resist it. Cooling removes thermal support. Turbulent mixing can either disrupt dense structures or add more material to them. Gravity eventually decides which concentrations survive. A dense region begins collapsing when its self-gravity becomes stronger than the pressure and motion supporting it. Astronomers often describe this using the Jeans condition, named after physicist James Jeans. The exact equation is not necessary here. Its basic message is that colder, denser gas can collapse in smaller pieces than hot, diffuse gas. Raise the density, and gravity has more matter to pull together inside a given volume. Lower the temperature, and the particles move less vigorously against that pull. The bow shock provides the initial increase in density. Radiation allows the gas to cool. Together, those changes lower the scale at which collapse can begin. Large compressed layers do not usually fall inward as one perfectly smooth object. Small irregularities grow. A slightly denser patch attracts additional gas. That increases its mass and strengthens its gravity, allowing it to collect even more. The layer fragments into clouds. Clouds fragment into smaller clumps. Within the densest cores, matter falls inward and forms protostars. A protostar is not yet a fully functioning star. It is a collapsing object that shines mainly because gravitational energy is being converted into heat. Gas continues falling onto it, often through a rotating disk. Only when the central temperature and pressure become high enough for sustained nuclear fusion does the object enter the main part of its stellar life. All of this takes time. The black hole passes first. The bow shock follows its movement. gas cools behind it, dense fragments develop, protostars form, bright young stars appear later. By then, RBH1 may be thousands of light years farther ahead. This delay is one reason the stellar wake is broad and complicated rather than a perfectly thin line marking the exact path of the event horizon. Stars form where the processed gas eventually collapses, not necessarily at the precise location where it first encountered the shock. The surrounding gas also has motion of its own. Turbulence pushes clouds sideways. Magnetic fields guide charged particles. Material entering from different angles develops different velocities. As a result, the visible trail can wander slightly even if the black hole follows a smooth route. The wake also changes speed as it extends toward GX. Near the leading tip, shocked gas has a projected velocity of around 300 kilometers per second. Farther downstream, the measured value decreases toward roughly 100 kilometers per second. The black hole itself is not slowing from 300 to 100 kilometers per second. These numbers describe the gas remaining behind it. After passing through the shock, that material begins mixing with the more slowly moving circumgalactic medium. Turbulent eddies form at the boundary between the fast wake and the surrounding gas. These eddies pull additional material into the flow. The process is called entrainment. Imagine stirring a spoon through a cup. The spoon moves first, but nearby liquid is dragged into motion. As a larger amount of liquid becomes involved, the original narrow flow spreads and slows. The conditions around RBH1 are very different from a cup of tea, but the mixing principle is related. Fast-shocked gas entrains slower surrounding material. Momentum becomes shared across a growing mass, and the average velocity falls. Recent three-dimensional simulations tested whether this process could reproduce the observed wake. The researchers included gravity, hydrodynamic motion, turbulence, and radiative cooling. When cooling was allowed, a coherent cold tail formed. The wake entrained surrounding gas and decelerated in a way that matched the observed velocity gradient. When radiative cooling was removed, the simulations did not produce the same long, organized cold structure. The hot gas mixed and dispersed too easily. It could not maintain the narrow tail seen behind RBH1. Cooling is therefore important for two connected reasons. It allows dense gas to survive inside the turbulent flow, and it helps the wake gather additional material from the surrounding medium. The trail may contain more gas than the black hole directly shocked along its central path. Turbulent mixing layers draw material inward from the sides, increasing the mass of the cool wake. This gives RBH1 access to a wider reservoir. The black hole does not need to pass directly through every gas particle that later becomes part of the trail. Its disturbance creates a flow that pulls surrounding material into the cooling region. The result resembles a narrow river gaining water from smaller streams, although no fixed riverbank confines it. Pressure, turbulence, cooling, and gravity define the boundaries. This also means the tail is not simply fading as it ages. In some regions, it may grow by collecting gas. The amount of cooling radiation should be connected to the rate at which material is entrained and slowed. The simulations make predictions about how the cooling luminosity should vary along the wake. Future observations can test those predictions by mapping faint emission from different temperature phases. Such measurements would turn RBH1 into a laboratory for a much broader problem. Astronomers see cold gas surviving inside hot environments throughout the universe. It appears in the halos of galaxies, the centers of galaxy clusters, supernova remnants, galactic winds, and streams moving through hot plasma. Cold clouds should sometimes evaporate or be torn apart quickly. Yet observations show that they can persist, grow, and travel considerable distances. Radiative turbulent mixing may explain how. Hot and cold material mix at their boundary, creating gas at an intermediate temperature. If that mixed gas cools quickly, it joins the cold phase rather than evaporating the original cloud. The cold material then gains mass. RBH1 offers an unusually clean test because the speed of the source, the length of the tail, and the gas velocity gradient can all be measured. The black hole creates a moving disturbance with a recognizable beginning and direction. Most astrophysical mixing layers are far less considerate. In a galaxy cluster, many clouds, jets, winds, and magnetic structures may overlap. It can be difficult to determine which material began where or how long it has been moving. RBH1 provides a long wake behind one compact source. The geometry allows simulations to be compared with observations more directly. The star formation adds another test. If cooling and entrainment are working as expected, the densest regions should produce young stellar populations at positions related to the travel time of the black hole. Their ages, masses, and distribution can reveal how quickly the shocked gas becomes capable of collapse. The first Hubble analysis found a general age progression along the trail. Stars farther from the current tip appeared older, as expected if RBH1 had passed those locations earlier. That pattern is not perfectly smooth, because star formation is not a factory conveyor belt. Some clouds begin denser than others. Cooling times vary. Turbulence delays collapse in one region and encourages it in another. A section encountered earlier may contain fewer visible stars than a section encountered later if the local gas supply was lower. Another region may experience a sudden burst after remaining dark for several million years. The average pattern still follows the black hole's direction of travel. The process is sometimes described as positive black hole feedback. Instead of suppressing star formation, the black hole helps trigger it. Positive feedback from a black hole is not entirely new. Jets from active galactic nuclei can strike clouds and compress them. Expanding bubbles can gather gas into dense shells. Outflows may create star formation along their boundaries. RBH1 is unusual because the black hole itself is moving through the gas. The compression front travels with it rather than being driven outward from a stationary galactic center. The distinction creates the long, narrow geometry. A jet can extend in a line, but it carries energy away from the black hole at an enormous speed and often produces strong radio emission. RBH1's trail contains a moving bow shock at the tip and a sequence of stellar populations behind it. A tidal tail can also form stars, but it is made from matter pulled out during a galactic interaction. It does not normally end in a compact supersonic shock powered by an invisible object. The measured morphology, gas velocities, and emission line ratios now support the runaway interpretation together. Energy provides an additional check. Maintaining a shock along such a large wake requires a substantial source of mechanical power. The moving black hole carries kinetic energy because it combines great mass with high velocity. As RBH1 gravitationally disturbs the gas, a small portion of that kinetic energy is transferred into motion, heat, turbulence, and radiation. Researchers compared the energy required by the wake with the energy available from a moving compact object. Their estimate indicates that the black hole must contain at least about 10 million solar masses. A less massive object travelling at the same speed would carry less kinetic energy and interact with gas less strongly. It would struggle to produce the observed shock over the estimated lifetime of the trail. This mass limit does not require RBH1 to lose most of its speed. The energy transferred to the wake is only a fraction of the enormous kinetic energy carried by a 10 million solar mass object. The black hole can power the disturbance for tens of millions of years while continuing forward at close to its original velocity. The surrounding medium is also thin enough that the accumulated drag remains limited. Gas receives a dramatic disturbance locally, but the total mass encountered is small compared with the black hole. From the gas's perspective, RBH1 is overwhelming. From the black hole's perspective, the gas is a light resistance spread across an immense distance. That contrast helps explain how the same encounter can strongly transform the material without bringing the runaway object to a stop. The shock does not convert every part of the gas into stars. Much of the material remains hot. Some mixes back into the circumgalactic medium. Some may cool without ever becoming gravitationally bound. Only a fraction reaches the densities required for star formation. Even within collapsing clouds, not all the gas becomes part of a star. young stars produce radiation, winds, and eventually supernova explosions. Those effects push away some of the remaining material and reduce the efficiency of the process. The visible trail, therefore, represents the successful portion of a much larger and messier interaction. Behind every bright cluster may be far more gas that was shocked, cooled, mixed, and dispersed without producing a permanent star. The surviving stars are easiest to see because the most massive members shine intensely in ultraviolet and visible light. Their radiation ionizes nearby hydrogen, adding more emission to the wake. This creates a second source of brightness after the original shock. The black hole first causes the gas to glow through heating and cooling. Later, newborn stars make surrounding gas glow through ultraviolet radiation. Spectroscopy can separate these contributions approximately by comparing the emission line ratios. Near the leading tip, shock ionization is especially important. Farther downstream, ordinary star formation becomes more prominent. The trail therefore changes in both age and energy source. At the front, gas is being processed now, in the time represented by the observation. Behind it, the shock occurred earlier, and stars have had time to form. Still farther back, the youngest massive stars have begun aging, exploding, or disappearing from view. Each position represents a different stage in the same sequence. RBH1 reaches undisturbed gas. A bow shock forms. The material heats and becomes ionized. Radiation carries energy away. Turbulent mixing adds more gas to the wake. Dense structures develop. Gravity begins collapse. Stars appear. The steps overlap rather than forming clean boundaries. Cooling begins while gas is still moving through the shock region. Mixing occurs while clouds are forming. New stars alter material that has not finished settling. The wake is a changing ecosystem of plasma, gas, dust, turbulence, gravity, and radiation. None of it requires the black hole to create matter. RBH1 supplies the disturbance, while the circumgalactic medium supplies the raw material. The phrase, awakening sleeping gas, describes a change in activity, not the creation of something from nothing. The gas was present around GX before the recoil. It may have remained diffuse for billions of years without forming many stars. The black hole gave part of that material a sudden route toward higher density. Once the compressed gas crossed the threshold for collapse, the process no longer depended directly on the nearby black hole. Gravity inside each cloud continued the work after RBH1 had travelled onward. That is why stars remain behind instead of following the runaway giant. They are born from local gas and remain in the gravitational environment where that gas collected. The black hole has already moved away before many of them begin shining. Along the 200,000 light-year trail, this sequence has happened repeatedly. Different clouds entered the bow shock at different times. Some produced only faint emission. Others became dense enough to form clusters containing large numbers of stars. The long line that looked like a scratch in Hubble's image is therefore not one object. It is a connected series of shocks, cooling regions, gas clouds, stellar nurseries, and young populations created during tens of millions of years of motion. The structure extends about 62 kiloparsecs in projection, or roughly 200,000 light-years. Spectroscopy shows that it contains a mixture of fast shocks and star-forming regions, while its colours are consistent with stellar populations becoming older with increasing distance from the active tip. These observations support a sequence in which RBH1 passes through the gas first and stars appear behind it later. Calling the whole structure a stellar nursery is accurate in a broad sense, but should not give the impression of one enormous cloud calmly producing stars from end to end at the same moment. The wake is closer to a chain of nurseries formed at different times. Near RBH1, the most recently disturbed gas has not had long to settle. The bow shock remains the dominant feature. Temperatures are high, velocities change sharply, and the emission from the gas carries the chemical signature of a fast radiative shock. Farther behind, the gas has had more time to cool and mix. Dense clumps have formed. gravity has begun pulling some of them inward. Still farther toward GX, the stars are older because the black hole passed those locations earlier. Some of the most massive stars may already have ended their lives while less massive members continue shining. This arrangement turns distance along the wake into a rough measure of time. It is not a perfect conversion. One cannot point to any position and calculate a precise age without additional measurements. The gas density changes along the route, cooling times vary, and star formation does not begin after one fixed delay. Even so, the general direction is clear. The youngest activity lies near the leading end, and earlier activity lies farther behind. Hubble first revealed that pattern through colour. Young massive stars tend to appear blue because their surfaces are extremely hot. They release much of their energy at short wavelengths, including ultraviolet light. Older stellar populations usually become redder after their most massive blue members disappear. By measuring the brightness of different parts of the trail through multiple filters, astronomers can compare its colours with models of evolving stars. The original analysis found that a simple model with increasing stellar age away from the tip provided a good fit. The exact ages depend on assumptions about dust, chemical composition, and the history of star formation, but the trend matched the motion of a runaway source. The stars that make the trail easy to detect are not necessarily the most common stars inside it. Massive blue stars are extremely bright. One of them can release far more light than a large collection of small, cool stars. A distant stellar population can therefore be visually dominated by a relatively small number of luminous members. Lower mass stars may also be forming throughout the wake. They are much fainter and difficult to separate individually at this distance. Astronomers have not counted every star in the trail, and the present observations do not provide a secure total census. Descriptions of millions of newborn stars should therefore be understood as an illustration of the potentially enormous population rather than a directly measured head count. What is firmly established is that the wake contains enough young stellar light to be a major feature. The original study estimated that the entire line was around 40% as luminous as GX in the measured bands. A structure that narrow was producing a surprising amount of light. That brightness comes from more than the stars themselves. Young massive stars release ultraviolet radiation that ionizes the hydrogen around them. An ionized hydrogen atom has lost its electron. When electrons later recombine with hydrogen nuclei or move between energy levels, the gas emits light at specific wavelengths. One of the most important lines is hydrogen alpha. It is commonly used to identify active star formation, because hot, short-lived stars provide the ultraviolet radiation needed to maintain large regions of ionized hydrogen. Oxygen contributes additional emission. The bright oxygen line at the leading end first helped reveal that something more energetic than ordinary star formation was occurring there. Webb later mapped hydrogen, oxygen, nitrogen, and sulfur across the bow shock region. Their combined line ratios showed that rapid shocks and cooling were present, while the broader wake contained material whose behaviour was increasingly connected with star formation. The young stars do not simply illuminate the gas, they begin changing it. Massive stars produce strong winds. Charged particles stream away from their surfaces at high speeds, carrying mass and energy into the surroundings. Ultraviolet radiation heats nearby material and can erode the edges of dense clouds. These effects may slow or stop the formation of additional stars in one region. They may also compress neighbouring material and encourage another dense clump to collapse. Star formation creates feedback of its own. A cloud begins by collapsing under gravity. Once stars appear, their radiation and winds push back against the same cloud. The most massive members then end their lives as supernovae, injecting another burst of energy. This limits the percentage of gas that becomes stars. A stellar nursery usually destroys or disperses much of its own remaining material before all of it can collapse. RBH1 begins the first large compression, but the stars formed behind it soon take over the local environment. A very massive star may survive for only a few million years. That is long enough for the black hole to travel thousands of light years farther along its route. When the star explodes, the bow shock that helped create its cloud is already far ahead. The supernova expands into the wake, heating gas and distributing newly formed elements. Elements such as oxygen were produced inside earlier stars. Still heavier nuclei can be created or dispersed during stellar explosions. Future generations of stars may form from gas enriched by that material. RBH, one's wake, can therefore develop its own local history. The first clouds are compressed by the black hole. Their stars alter nearby gas. Some of those stars explode. The explosions distribute energy and elements through the trail. Whether this activity triggers further star formation or disperses the remaining gas depends on local conditions. A supernova shock entering a dense cloud may compress it. The same explosion entering thin gas may simply push the material apart. The trail is too distant for astronomers to follow these individual events directly. They see the combined light from populations spread across enormous regions. Future observations may separate more of the stellar knots and determine their approximate masses and ages. Infrared measurements can reveal stars hidden by dust, while deeper spectra can measure the movement and chemical composition of the gas. At present, the nursery is known mainly through its large-scale structure. That scale remains difficult to absorb. 200,000 light-years is not the distance from the black hole to one unusually remote cluster. It is the full projected length of a connected wake, pointing from GX toward the moving source. Light entering the trail near GX would require about 200,000 years to reach its outer end if it travelled along the projected length. RB81 requires tens of millions of years because it moves far more slowly than light. The wake is longer than the bright stellar disk of the Milky Way. It is also extremely narrow compared with its length. A feature with those proportions is difficult to produce through ordinary star formation. Galaxies form stars across disks, rings, central bursts and irregular clouds. Tidal interactions can create long streams, but those streams are usually broader and more complex. RBH1 provides a moving point of compression. The black hole advances along one route, while the shock and cooling flow organize gas behind it. The stars inherit that narrow geometry because their parent clouds formed inside the wake. They do not remain perfectly confined forever. Once a star has formed, it follows gravity like any other star. The stellar groups may possess small velocities relative to one another. Their parent gas can move sideways, and the gravity of GX and its dark matter halo can alter their paths. Over long periods, clusters may expand. Stars may drift away from their original neighbours. Some groups may remain gravitationally bound, while others disperse into loose associations. A bound star cluster contains enough mass for its members to remain together despite their internal movement. An unbound association spreads as its stars continue along slightly different paths. The efficiency of star formation affects which result occurs. If a cloud converts a large fraction of its mass into stars before the remaining gas is expelled, the stellar group has a better chance of staying bound. If most of the original mass remains in gas and is quickly removed by radiation or supernovae, the stars lose part of the gravity holding them together and may separate. RBH1's trail could therefore produce a mixture of compact clusters and scattered stars. Some may remain in the extended halo of GX. Others may become genuine intergalactic stars, living far from the bright body of any galaxy. Intergalactic stars are not entirely unknown. Galaxy collisions and gravitational encounters can throw stars out of their original systems. Large galaxy clusters contain diffuse light, produced by stars moving between individual galaxies. The stars behind RBH1 would have a different origin. They were not necessarily born inside a normal galactic disk and later removed. Some may have formed directly in circumgalactic or intergalactic gas after the black hole compressed it. This gives them an unusual birthplace, but it does not make them physically different from other stars. Hydrogen still fuses into helium inside their cores. Their lifetimes depend mainly on their masses and chemical compositions. Small stars can survive for billions or even trillions of years, while massive stars use their fuel quickly. A low-mass star formed in the wake could remain long after the bright blue trail had disappeared. By then, GX might have changed beyond recognition. It could merge with another galaxy, form new structures, or become part of a larger system. RBH1 might be millions of light-years away. The surviving wake stars would preserve evidence of the event through their ages, chemical compositions, and motion. Whether future astronomers inside that distant system could reconstruct their origin is another question. They would need to recognize that a narrow population of stars had formed during a brief passage of an ejected black hole. The trail looks obvious to us because we see it while its youngest stars still shine brightly. That visibility will not last. Massive blue stars age quickly. As they disappear, the wake will become redder and fainter. Emission from ionized gas will weaken when there are fewer ultraviolet photons and when the gas disperses. The narrow line seen by Hubble may eventually lose its contrast against the dark background. The stars will not vanish, but the trail will become harder to identify as one connected feature. This is another reason the discovery required good timing. We observe the system during a period when the wake is mature enough to extend across 200,000 light-years, but young enough to contain bright, short-lived stars. Earlier, the trail would have been shorter. Much later, it may become too faint and dispersed to recognize. RBH1 has provided a visible record during a limited stage of a much longer journey. The nursery also reveals how much ordinary matter exists outside the bright parts of galaxies. The circumgalactic medium is difficult to observe because its gas is spread thinly. A large amount of matter can remain nearly invisible when it is not forming stars or emitting strongly. RBH1 compresses and heats part of that gas, making it detectable. The wake therefore outlines material that was already present around GX. It does not contain only matter carried out by the black hole. The recent hydrodynamic modelling suggests that radiative mixing allows the cold tail to entrain additional material from the surrounding hot medium. The observed decrease in gas velocity along the wake can be reproduced when the flow gains mass through this cooling and mixing. Without radiative cooling, the simulations do not form the same coherent cold tail. This means part of the nursery may be assembled from gas drawn into the wake from the sides. The black hole passes through a central corridor, but turbulence expands the region of influence. Hot and cold material mix at their boundary. If the mixed gas cools quickly, it joins the cold phase instead of evaporating the existing clouds. The wake can gain material as it develops. That extra gas provides more fuel for star formation than a simple calculation, based only on the black hole's narrow path, might suggest. RBH1 behaves less like a needle-making hole and more like a moving disturbance that gathers nearby material into a longer flow. The comparison still has limits. A normal wake eventually fades through friction and mixing. This wake can convert some of its gas into stars, creating objects that continue existing after the original flow disperses. Stars are durable records compared with glowing plasma. A cloud can cool, expand, or become invisible. A star can remain detectable for billions of years. The nursery also raises questions about the distribution of stellar masses. When stars form in ordinary molecular clouds, they appear across a broad range of masses. Small red dwarfs are much more common than massive blue stars. The same may be true in RBH1's wake, but the conditions are unusual. Pressure is high behind the shock. Turbulence is strong. The gas may cool rapidly from a very hot phase. The chemical composition and magnetic environment may differ from those in a normal galactic disk. Those conditions could influence how clouds fragment and which stellar masses become common. Current observations cannot yet determine the complete initial mass function of the wake. That term describes the distribution of stellar masses at birth. Establishing it would require measurements sensitive to fainter, lower-mass stars. At the system's distance, even Webb cannot count them individually across the full structure. Astronomers can instead study the combined spectrum and colour of each region. Models can then estimate the mixture of stars likely to be present. These estimates remain dependent on assumptions, but they can test whether the wake behaves like familiar star-forming environments or produces a noticeably different population. The same observations may reveal how efficiently shocked circumgalactic gas turns into stars. The bow shock processes a certain amount of material. Only part of it cools. Only part of the cooled gas becomes gravitationally unstable. Only part of each collapsing cloud becomes stellar mass. Measuring those fractions would help astronomers understand positive black hole feedback under conditions rarely observed elsewhere. Most black hole feedback studies focus on an active nucleus at the centre of a galaxy. Radiation, winds, or jets move outward from that fixed source. RBH1 reverses the geometry. The black hole moves while the affected gas remains behind. This allows distance to preserve a sequence of events. Near the tip, astronomers can study the shock. Farther back, they can examine cooling and mixing. Beyond that, they can observe star-forming clouds and older stellar populations. It is almost an astrophysical experiment laid out across space, although no one arranged the variables or provided a control group. The length of the wake gives researchers many stages to compare. One region may show strong oxygen emission and little stellar continuum. Another may show young blue stars with less evidence of active shock heating. A farther region may contain an older population and slower gas. Together, these areas describe how the environment changes after the black hole passes. There are still uncertainties. The precise mass of RBH1 is not known, although the energy of the shock provides a lower limit of about 10 million solar masses. The complete three-dimensional distribution of gas is not mapped. The total number and mass of stars in the wake have not been measured directly. Those gaps do not erase the central conclusion. A supersonic, supermassive black hole is driving a radiative bow shock through gas around GX. The wake contains young stars, and their overall age pattern follows the direction expected from the black hole's motion. The object normally associated with swallowing matter has produced conditions in which dispersed matter can gather. Nothing about that outcome makes RBH1 safe or gentle. A star approaching too close would still be torn apart or captured. Gas crossing the event horizon would still disappear from the observable universe. The nursery exists because most of the gas does not approach that closely. It encounters the black hole's wider gravitational influence, passes through the shock, and remains outside. Distance determines whether the result is capture, heating, deflection, compression, or collapse. The same object can therefore destroy matter in one region while helping organize it in another. This is not a contradiction. It is a consequence of gravity acting across different scales. Near the event horizon, escape becomes impossible. Thousands of light years away, the moving gravitational field can redirect gas without consuming it. Farther downstream, the black hole is gone, but the disturbed material continues responding. By the time a star begins nuclear fusion, BH1 may no longer have any direct effect on it. The black hole started the chain and moved on. That chain has produced a stellar structure larger than the Milky Way's bright disk, not by releasing creative energy from inside the event horizon, but by turning motion into shock pressure and allowing ordinary gas physics to proceed. The nursery is therefore the most visible part of a much longer causal sequence. Two galaxies collided. Their central black holes merged. Gravitational waves kicked the remnant away. The remnant crossed the surrounding gas. A bow shock compressed that gas. Cooling and gravity then formed stars. Remove any major step, and the blue trail does not appear. The unusual result came from processes normally discussed separately: galaxy evolution, gravitational waves, black hole dynamics, shock physics, turbulent mixing, gas cooling, and star formation all became parts of one event. That is why RBH1 is more than an unusual black hole or a long collection of young stars. It connects the violent physics near merging event horizons with the ordinary birth of stars tens of thousands of light-years away. The connection also asks us to reconsider the simple role often assigned to black holes. Black holes earn their destructive reputation honestly. A star passing too close can be stretched by tidal gravity until it is torn apart. Gas falling toward an event horizon can form a hot disk, release enormous amounts of radiation, and then disappear beyond the boundary from which light cannot escape. Jets launched from the surroundings of an active black hole can cross entire galaxies. Powerful winds can heat cold gas or push it away, reducing the amount available to form stars. At the center of a galaxy cluster, an active, supermassive black hole can inflate vast bubbles inside the surrounding hot plasma. These outbursts may prevent gas from cooling and slow the growth of new stars. There is no shortage of evidence that black holes can disrupt their environments. The problem begins when that behavior is reduced to a single rule. A black hole does not automatically destroy everything nearby. The result depends on distance, motion, gas density, temperature, and the way energy is transferred. A cloud heated and dispersed by a jet will form fewer stars. A different cloud compressed at the edge of the same jet may form more. Gas driven out of a galaxy can stop participating in star formation there. If that gas later cools and falls back, it may support another period of growth. Black hole feedback is not a simple switch between creation and destruction. It is a collection of processes acting under changing conditions. RBH1 provides one of the clearest examples because the geometry is easy to understand. The black hole travels through gas. A bow shock forms in front of it. The gas heats, ionizes, and changes direction. Radiation removes part of the heat. Turbulent mixing draws more material into the flow. Dense regions become gravitationally unstable, and stars form after the black hole is moved ahead. The black hole does not create the raw material. It does not assemble stars directly, and it does not choose a useful speed. Its movement changes the physical state of gas that was already present. Calling RBH1 a creator is therefore a convenient summary, not a literal description of intention or construction. The actual creator of each star is gravitational collapse inside a gas cloud. The black hole supplies the unusual event that makes that collapse possible. A falling stone can compress soil without understanding agriculture. A storm can move sediment and create new land without planning a coastline. RBH1 can trigger star formation without possessing any purpose. This distinction does not make the result less impressive. It makes the physics clearer. The story begins with events that appear completely destructive. Two galaxies collided and lost their original forms. Their central black holes spiraled together. Part of the binary's mass energy left as gravitational waves. The merged remnant received a recoil powerful enough to remove it from the center of GX. The galaxy was left without the supermassive black hole it had spent millions of years bringing into the same nucleus. Each stage involved disruption. Yet the final consequence included a narrow trail of young stars. The sequence shows how one physical event can change roles as energy moves from one scale to another. Close to the merging black holes, energy left as gravitational radiation. At the galactic scale, the uneven momentum of that radiation accelerated the remnant. In the circumgalactic medium, the remnant's kinetic energy produced a shock. Inside the wake, part of the shock energy became heat and turbulence. Radiation then carried enough heat away for compressed gas to remain dense. Gravity converted part of that material into stars. No stage violates the destructive behavior of black holes. The energy simply produces different outcomes in different environments. The same pattern appears elsewhere in astronomy. A supernova destroys a star, but the explosion distributes oxygen, silicon, iron, and other elements. Those elements later become parts of new stars, planets, atmospheres, and living organisms. A galaxy collision distorts or destroys the original galactic structures, yet it can compress gas and trigger a starburst. Massive stars release radiation that erodes their birth clouds, but the expanding pressure fronts can also squeeze nearby gas into new dense regions. Creation in astronomy often follows disruption, because matter and energy are reorganized rather than removed from existence. Black holes make this relationship feel more extreme because material crossing the event horizon becomes inaccessible to outside observers. Even there, the black hole's mass and spin still affect the surrounding universe. RBH1 does most of its creative work far outside the horizon. The difference between capture and compression is mainly one of distance. Gas passing extremely close can be swallowed. Gas passing farther away can be deflected. Gas across a still larger region can be shocked by the collective flow. The bow shock reaches thousands of light years across, while the event horizon occupies a far smaller scale. The visible nursery therefore contains gas that avoided destruction. It remained outside the black hole, lost heat, and became dense enough for gravity to act. This gives the title of creator a slightly unusual meaning. RBH1 creates opportunity rather than material. It takes gas that was too thin to collapse efficiently and places some of it in conditions where collapse becomes possible. The black hole's speed is essential. A stationary supermassive black hole inside thin circumgalactic gas would not create the same long wake. Gas could fall toward it more symmetrically, perhaps forming a weak accretion flow. RBH1 encounters new material continuously. Its supersonic movement forces the gas through a one-directional shock and leaves the processed material behind. The recoil transformed a central black hole into a travelling feedback source. That may be the most unusual feature of the discovery. Supermassive black holes normally influence galaxies from their centres. Their radiation and jets travel outward, but the black holes themselves remain close to the same location. RBH1 carries its gravitational influence across the circumgalactic medium. Each part of the trail is affected for a limited time. The black hole arrives, disturbs the gas, and leaves. The region then continues developing without it. This movement allows the positive effect to extend across 200,000 light years. A fixed shock might compress one shell or cloud. RBH1 continually generates a new leading edge. The trail grows as long as suitable gas remains ahead and cooling remains efficient behind. Eventually, those conditions may change. The black hole may enter a region where the gas is too thin to form a visible wake. It may cross material that is too hot or too diffuse to cool quickly. The trail could then weaken or disappear, even while RBH1 continues moving. This means the visible nursery may represent only part of the black hole's total path. The section near GX may also be incomplete. Gas in the merger remnant was denser and more turbulent, making the earliest wake difficult to preserve as a narrow feature. Hubble shows the part of the journey where the environment made the consequences easiest to recognize. Other runaway, supermassive black holes may be moving through less favourable surroundings. They would remain dark unless they carried an active accretion disk, disturbed nearby stars, or crossed enough gas to create a visible shock. RBH1 may be the first confirmed example, not because it is the first to exist, but because its path produced an unusually clear signal. The discovery therefore suggests a new way to search for hidden black holes. Instead of looking only for a bright displaced nucleus, astronomers can search for long, narrow wakes containing a leading shock and a stellar age pattern. A candidate trail would need careful testing. Jets, tidal streams, edge-on galaxies, gravitationally lensed arcs, and detector artifacts can all create elongated features. Spectroscopy can determine whether the structure is physically connected, whether the gas contains shocks, and whether the velocity changes fit a bow shock. Deep imaging can test the stellar colours. Infrared observations can reveal obscured regions. Radio and X-ray measurements can check for a conventional jet or active nucleus. RBH1 provides a template, although future objects may not look exactly the same. A slower black hole would create a different shock. A more massive one could disturb a wider region. A path through denser gas might produce a brighter but shorter wake. Some recoiling black holes may remain bound to their galaxies and create curved or repeated disturbances as they move through the centre several times. Others may escape without forming any stars. Finding more examples will show whether RBH1 represents a common phase or an exceptionally fortunate combination of circumstances. The object also provides evidence that gravitational wave recoil can affect galaxy evolution in a direct and visible way. Before this system, strong kicks were well established in numerical calculations. General relativity allowed them, and simulations showed how unequal masses and misaligned spins could produce large velocities. RBH1 connects those calculations to an object travelling far from its former nucleus. Its measured speed and long wake support emerge roughly 70 million years before the observed stage. Analysis of the recoil indicates that the progenitor binary was probably precessing, that its mass ratio was no more extreme than about 6:1, and that the larger black hole had a substantial spin. The same work suggests that GX likely formed through a major gas-rich galaxy merger. This allows astronomers to study a black hole merger without having recorded its gravitational waves. The current motion of the remnant contains information about the earlier binary. The trail provides a travel distance and direction. The bow shock provides a velocity. Numerical relativity models connect that velocity with possible mass ratios and spins. It is an unusual form of historical reconstruction. The merger itself ended tens of millions of years before the light we now observe left the system, but its momentum remains preserved in the runaway black hole. Future gravitational wave observatories may observe similar events directly. A detector such as LISA is intended to measure low-frequency gravitational waves from massive black hole binaries. If a system similar to the progenitor of RBH1 merges during the mission era, astronomers could measure its masses and spins from the waves and predict the recoil. Later, electromagnetic observations could search for a displaced remnant. In the most favourable cases, researchers might follow the same event from inspiral to merger, recoil, and interaction with surrounding gas. RBH1 gives a preview of the final stage. The discovery also changes what astronomers may expect to find at galactic centres. A galaxy formed through a major merger would normally be expected to contain the black hole created when its two central black holes combined. If the remnant receives a strong kick, that expectation fails. The galaxy may retain a dense stellar centre while losing its central supermassive black hole. Its later star formation and feedback history can then differ from those of a galaxy that kept its remnant. In smaller galaxies, where escape velocities are lower, even moderate kicks may remove black holes more easily. Repeated ejections across cosmic history could affect the number of galaxies that retain central black holes. RBH1 represents one especially dramatic case because the expelled object left a visible record. GX also loses more than a central mass. A supermassive black hole can regulate gas through active periods. Without it, the centre may receive less heating from black hole winds and jets. That does not guarantee increased star formation. Supernovae, stellar winds, gas dynamics, and later mergers continue affecting the galaxy. The absence changes one part of a complicated system, rather than determining a simple outcome. Meanwhile, RBH1 transfers some of its kinetic energy into gas outside the galaxy. The black hole's removal may reduce feedback in the centre, while creating positive feedback along its escape route. One event therefore redistributes black hole influence from the nucleus into the surrounding medium. This redistribution is another reason the labels destroyer and creator are incomplete. RBH1 can reduce one kind of activity in GX and increase another kind of activity in the wake. It can capture a small quantity of gas while compressing much more. It can heat material at the shock and create the conditions for cooling farther behind. Which description applies depends on where and when we look. At the leading edge, it is a source of violent heating. Inside a collapsing cloud downstream, it is the earlier cause of compression. Near the event horizon, it remains an object from which light cannot escape. Across the full trail, it becomes the moving origin of a stellar nursery. Science often replaces simple categories with conditional explanations. The discovery did not prove that black holes are secretly helpful. It showed that a process associated with black holes can have several effects. That is a more useful conclusion because it can be tested. Astronomers can measure how much gas is shocked, how quickly it cools, how the velocity changes, and where stars appear. Simulations can vary the black hole speed, mass, gas density, and cooling rate. Their results can then be compared with the observed structure. The recent hydrodynamic work already shows that radiative cooling is necessary to reproduce the coherent cold tail, and that turbulent entrainment can account for the downstream deceleration. Future observations can test additional predictions. A detailed map of the cooling radiation should show how energy is lost along the wake. Better stellar measurements should reveal the age distribution more accurately. Gas density estimates could determine how efficiently the bow shock turns circumgalactic material into cold clouds. The exact mass of RBH1 may be constrained more tightly if astronomers detect matter bound close to it or improve the energy model of the wake. Researchers may also look for an old compact star cluster travelling with the black hole. Some stars orbiting very close to the original binary could have remained attached after the recoil. Finding such a cluster would provide another way to estimate the black hole's mass and history. No such measurement is required for the present confirmation. The bow shock already provides the central dynamical evidence. A sharp velocity change of around 600 kilometres per second appears across the tip. The downstream flow, shock geometry, and emission line ratios fit a supersonic source moving near 954 kilometres per second. Energy conservation implies a black hole mass of at least 10 million suns. Those numbers transform the blue streak from a visual curiosity into a physical system. The thin line began as something that looked like a cosmic ray strike on Hubble's detector. It survived the first checks, appeared in separate filters, and pointed toward a compact galaxy. Keck showed that the galaxy and trail were at the same redshift. The spectra revealed both star formation and shocks. Hubble's colours suggested an age progression. Webb then resolved the leading gas strongly enough to expose the bow shock. The explanation became stronger because different instruments measured different parts of the same process. Hubble supplied structure and colour. Keck supplied early spectroscopy. Webb supplied detailed velocity and ionization maps. Numerical relativity explained the recoil. Hydrodynamic simulations explain the cooling and deceleration in the tail. No single observation carries the entire story. The discovery depends on several independent lines of evidence agreeing. This is how an object that cannot be seen directly becomes real in astronomy. RBH1 remains dark, but its speed appears in the gas velocity. Its mass appears in the energy needed to power the wake. Its direction appears in the long stellar trail. Its origin appears in the recoil calculations, and its influence appears in newborn stars. The invisible object becomes one of the most thoroughly connected parts of the system, because everything around it responds. There is still room for uncertainty. The black hole's exact mass is not known. The complete stellar population has not been counted. Its future trajectory through the wider halo remains uncertain. Astronomers will revise details as new observations arrive. The central picture is now much more secure than it was when the trail was first reported as a candidate. RBH1 is a supersonic runaway supermassive black hole producing a bow shock and a long cooling wake behind it. That picture brings us back to the apparently wrong sentence with which we began. A black hole is creating stars. Now the meaning is clearer. RBH1 does not reach into the gas and assemble stars. It does not release material from inside itself. It does not reverse the physical laws that make black holes dangerous. It moves quickly enough to compress diffuse gas. The gas radiates heat. Gravity forms stars from the cooled material. The result depends as much on the environment as on the black hole. Had the recoil pointed into emptier space, the same object might have crossed the darkness without leaving a visible line. Had the gas failed to cool, the wake might have remained hot and dispersed. The nursery exists because the mass, speed, direction, gas supply and cooling conditions occurred together. That combination lasted long enough to produce a trail larger than a galaxy. Somewhere inside the wake, massive blue stars are consuming their fuel quickly. Smaller stars are beginning much longer lives. Gas clouds are being eroded by radiation, while other dense clumps may still be collapsing. At the front, RBH1 continues into new material. Behind it, the earliest stars in the trail are already aging. Farther back, GX remains at the end of the line, carrying the evidence of the merger that launched the black hole. The complete system records several times at once. GX shows the former home. The older wake shows the early journey. The young tip shows the latest interaction. The black hole points toward what comes next. We see all of these stages in one image because light from each part has crossed nearly the same enormous distance to reach us. The events themselves unfolded over around 70 million years, and here, in a much quieter place, we have followed them in a little less time than that. Before we leave the trail, consider where you are listening from now. Perhaps the room is darker than when we began. Perhaps the clock has moved farther than expected. Or perhaps these minutes have passed slowly. RBH1 has travelled tens of thousands of kilometres during every minute of this narration, at least in the distant period represented by the light we observe. The stars behind it will remain long after the shock has moved on. If this journey through colliding galaxies, gravitational waves, runaway black holes, and newborn stars has helped you settle, you can give the video a like and subscribe to Science for Sleep. It helps this quiet collection of science reach other people who prefer their supermassive cosmic events delivered at a reasonable volume. Tonight, we began with a black hole known for what such objects can take away. We found one that was expelled from its galaxy, crossed a thin reservoir of gas, and left new stars where almost none might otherwise have formed. It is still a black hole. Anything crossing its event horizon will not return. Its gravity remains extreme, and the merger that created it was one of the most violent events in the universe. Yet along a narrow path behind it, gas has cooled, clouds have collapsed, and stars have begun shining. The destroyer did not stop destroying. Under these particular conditions, its movement also gave matter another way to gather. For now, RBH1 continues forward, the bow shock remains ahead, and the long blue trail stays behind as a record of where an invisible giant once passed. Sleep well, fellow traveller, wherever you are listening from tonight.